Start video? Yes, start video, not video? That's this camera or what?
I think you should disable the microphone.
He just asked me to turn it on, no?
I'll try turning off.
Oh, sorry about this. I didn't realize it was going to be so complicated. Are we now live? Yeah.
Can you hide this one?
Why? What do you want to do? Oh,
Hide it.
okay.
You want to capture this video?
You want to move on the right?
I mean, you can hide this one because we are capturing this.
Okay.
Should be okay because it doesn't.
No, well, let's
doesn't
see.
cover
What do you
the
want?
Slides.
Oh, yeah.
It's trouble. I don't want it, in fact, here. Do you know how to drive this thing?
Just leave it.
Well, it's going to cover the screen.
Yeah, this was
Just a
okay.
little
Now it's okay.
straight.
Well, except that I need to be full screen. Okay, it's approximately.
Go to the first slide. The first slide.
Let me just, yeah.
Okay. Okay, good.
Okay, good morning, everybody. People coming to this last day of the conference, and today with the pleasure and the honor to introduce Professor Carlos Dele from Imperial College, and he's going to speak about gravity localization on brakes.
Very well. Happy. Sorry about the delay of the electronics.
Didn't realize. I mean, 3 months ago. The broadcast all around. I want to talk about some issues, not so much something with alcohol and so forth, but this is really just part of the general kind of top-down, purely today within supergravity context. People who have heat parking they often know how to talk that language, but this day we're definitely going to look at classical solutions and see there's some of the solutions of supergravity possibly have use in lower dimensions. So this is the issue, whether you can get gravity to localize on generalized membranes. Work with a variety of power thin countries with Copa originally, and my students out of Carol and Eric and London, and more recently with my two new Chinese students on Who's actually from Hong Kong, and again in Taiwan. I have a growing number of Chinese students in my environment. So what about we call taxonomy? That's the division of the topic into two broad categories. So this is going to be talk about generalized membrane solutions, or what we call brains. And there are basically two taxonomies, which it means basically going to be divided by the boundary conditions you have to do with the solution. And if you look at fluctuations around that, the various boundary conditions you can impose on the equations, and you get different types of behavior. So that's the first distinction that I want to make for you. So the first type here is what I call collusive kind of reductions, or consistent reductions from the higher dimensional theory to the lower dimensional theory. And when you use the brain solution in the background, this is kind of a skeleton on which these fluctuations can propagate. So what we've been discovering is that if the brain solution that we start with has unbroken supersymmetries, then actually we'll get a world volume theory. I'm going to talk basically about flat world volumes to start with. So you can look at small ADM type fluctuations, and there was spin 2 and the associated fields according to that supersymmetry. And this will build a supergravity. That's type 1. Type 2 is similar but different. This is a full localization, and I'll have to explain the word full, of gravity near, not necessarily on, but near, on and nearby the brain, the underlying brain, but then falling off. As you go towards, there will be transverse infinity. By the way, this is not exactly equivalent to time, it's just that I'm not making the transverse space compact. It can go completely infinitely away. And so there were gravitational phenomena that are strong near the brain but fall away. This is what you would think of as the natural localization of gravity. And this generates a massless effect of lower dimension theory, but it is not a technically consistent reduction, unlike the black hole. And so, as I said, the distinction between these two depends upon the choice of boundary conditions for fluctuations near the brain volume. Okay, so let's look at type 1. These are the consistent reductions. And actually, we've started to realize that one can do this for some time, going back to a paper by Brecker and Perry. And that first of all, you have a solution of the underlying supergravity theory, reaching answers and so forth. And with the very low volume being flat, just but you can replace flat by reaching flat. That is to say, you can replace the world volume metric by any solution for which the reaching center vanishes, and that's still a perfectly good solution of the whole higher dimension theory. So we have a skeleton unit. Now the flat world volume metric can be promoted to a reaching world volume metric. And of course, as soon as Stephen Hawking heard about that, first thing he did was the solution on the world volume. Now, of course, this too, to come back to the word full, which this is not. It is a perfectly consistent reduction, but the way it works is that the skeleton, the background solution into the higher dimension, we're not touching that. We're messing with the world volume and promoting a flat world volume to reach a flat world volume. But actually, the higher dimensions is still there. So basically, whatever you do on the world volume, just top it up. So, for example, in the case of Stephen Hawking first jumped on with a black hole on there, they had a 5-dimensional system not based upon atoms, random something. And then, of course, when you have a black hole in 4 dimensions, and then you remember fifth dimension, it's there. You're not doing anything with it, but it's there. So the black hole looks like a string. So that's the sense in which this is not exactly a concentration of gravity, it is a full dimensional reduction. And now, okay, so then on to supersymmetry, and in particular in the Randall-Simon context, the one that was also related to the paper by Chan and Paul, that if there's a surviving supersymmetry of the starting entity, the quiet one, then that can be promoted to a supergravity field. You get fermionic particles. And in fact, we've been realizing that this generalizes quite a lot. We think it's a theorem that this all happens. So far, we've accumulated a family of examples of this. We don't actually have proof, but it looks like this is the situation. And in fact, this gets involved with other types of mathematics. In particular, we've been talking to Dan Waldron, and techniques of generalized geometry come into this. So I think there's quite a lot of interesting developments still to be made about it. Just to come back to how the original Ricci flatness works. If you start with a toy model with in some higher dimension space with gravity, a scalar field, and a form field, and typically for brain solutions, you say the scalar field is interacting with the form field. And then you consider a warped brain solution ansatz, with the x being the world volume directions, the y's being the transverse, and with warp factors depending only on the y's. And then you calculate the Ricci tensor in the world volume and the transverse directions, and then because this is a warped product, the off diagonal mu I components of the Ricci tensor vanish. So you have this structure. In fact, you see the del squared is a derivative with respect to the transverse skeleton metric. And basically, when you've seen the structure of the Ricci tensor, you realize that in fact you can focus on these world volume directions. As long as the relations between the A and B functions here are the ones that you know already work in the skeleton, and let them be, then the original piece of here is the Ricci tensor, you set that to 0, you're good to go. So that's basically the structure here. You can also do it in the transverse space, but that's more than I want to talk about. today. If you do it both on the world line, there's transverse plate, there's structure that we call doubling, and they work too. So that's type one. Okay, now, I've said here that can be extended to supergravity if the underlying solution has an unbroken supersymmetry. We think this is a pretty general situation. The key to how you figure, basically, with any story of consistent reductions, you first have to have an idea. You think of what your ansatz is, and then you check it. On the other hand, if you go for a walk in Shanghai and somebody comes up to you now and hands you a piece of paper with a suggestion, you can just check it and go away for lunch right away. You don't have to do any more work. It's just a check. And it works. Okay. So we have to figure out the ansatz for extending it to the Fermat components. And actually, that's what we're doing with Jimmy. It's even fun, but it looks like this is a general situation. Okay, now I want to come to a situation that actually reveals the two taxonomies. I mentioned type one, which is consistent reductions. And this is an interesting case. This is the first one when we started to see that there's more possibility. So let's go back to the model that Solomon Setkin constructed back in 1984. So this is actually six-dimensional minimal supergravity coupled to a two-form potential multiplet and also a supermaxwell multiplet. Gauging is an R symmetry, that's kind of the chiral symmetry of the theory. So that's what you start with in 6 dimensions. Doesn't sound so exceptional. It's gauging an R symmetry turns out to be important. Because here's what you get for the bosonic part of the Lagrangian. And typically, as I do with my students in activity theory, when we start talking about supergravity, we get lazy and throw the fermions away as much as possible. Let's look at the background solution of the bosonic. So let's start with just the bosonic part of the action. Given here, Einstein, I figured out the middle. So there's a freeform scalar. And now this final term, it's a scalar potential, but notice the sign action. Kinetic minus potential energy. That's a power potential. Actually, that's unusual in gravity construction. You get a power potential. That's going to be a key to what happens at the moment. And then there's a mixed field strength. So this gives rise, first of all, because this is a kind of exponential potential, this phi scalar field doesn't like sitting quietly. If you try to make the world volume 6 dimensions flat, it says no thanks. This guy wants to run in range. So flat 6-dimensional spacetime is not a solution of this. But you can have a scalar field running that compensate by kind of a cosmological constant, and then supergravity can say, oh, now we know. In fact, this gives rise to a family of solutions with non-compact symmetries, and you can generalize this simple model to systems with SOPQ over SOP process. You notice these are non-compact symmetries where non-compact repeated several times. Non-compact transverse space, non-compact symmetry. It's actually a whole new family of symmetries that typically have not been considered in supergravity production. Precisely because some of the occurrence non-compact spaces humans roll well, but we come to it. Okay, so what does it allow? It doesn't allow 6-dimensional flat, but it will accept 4-dimensional Minkowski across a 2-sphere. Even that possible stuff play. And if you turn on flux for the vector field, a U1 monopole, turned on in the 2-sphere directions, and here in fact you see the solution that Solomon says we found. Okay, so with the flat world volume, the 2-sphere, and the vector field turned on. This is a supersymmetric solution preserving a unbroken solution. Okay, so that's where we start with. Now, this is within supergravity theory. Either you type 2A or type 2B. It's easier for me, first of all, to lift it, to rewrite it. Old jokes about dimension reduction. Warren Seal, I think, the origin, many of the jokes in physics. The inverse of reduction is oxidation. Oxidation, and then until the all the evidence of physical review got a hold of this to say you can't reproduce the so it's become literally modern political correct parlance. Anyway, we write it in 10 dimensions, and here's what it looks like. So now, of course, there are extra dimensions, and this little, you start to see what the transfer space knits together in order. It's interesting. This DS4 bar square that's hiding here is actually an interesting part of it. QGC2024. What a non-compact version of the gravitational models. So that's interesting that that comes up. And then there are a couple of naturally compact directions too. There's circles in there. So that's just lifting it back up to 10 dimensions. You can also lift it into type 2B. Now, this solution admits the supergravity on its world volume. That's exactly what I've been telling you about. And a consistent reduction step. So this, again, I'm being lazy and showing you the bosonic part of the embedding. Here we generalize the world volume metric and so forth and forms to an interacting theory on the world volumes, and since it still works, okay? So you have 8 superchargers, 8 symmetries of the static solution become 8 symmetries of the world volume theory, and you can lift it up, and it has the world supergravity on the world volume perfectly consistent within the higher dimension. And this suggests there's also a D3 branch that works in a similar way to the units. We got a family, growing family example. It's happening in physics general phenomenon. But we don't have to prove it. And that's where it's happening in the only problems that come in. You could also do M5 brain, the 6-dimensional world volume. Similarly, you can embed n equals 4, 0 supergravity on the world volume. Now, an 11-dimensional theory, the M5 brain. And similarly, you can make such an embedding. We're trying to extend this to the fermionic sector. So that's about the type 1. That's on consistent reduction with full supergravity and growing up on the world volume. But maybe not fully localized because they sort of get just copied with the higher directions. We're only allowing the fluctuations, vibrations to go profile. Okay, now about the whole issue of consistent truncation. So we started with a skeleton, and the consistent truncations allow arbitrary solutions to be realized as exact solutions of apparent higher dimension. And you can have black hole brains and all sorts of fun things that you might want to do otherwise. Now, there's an issue that comes up because Chris Hall and Nick Warner are going to start talking in the back of the room and say, wait a minute, we talked about this back in the 1880s, you've got a problem, which is transfer space is infinite volume. And when you come to ask about the guy who wanted the apple fall in his mother's garden in Wolfsburg, the town of Cambridge, right? Margaret Thatcher comes from there. He had Isaac Newton, like Wisconsin. You write it in the world of lower dimension from compactifications of you notice that the Newton constant involves the inverse of the volume of the transfer space. Transfer space is infinite. Hey, Newton equals 0. Newton's constant is 0. So what happened to all of that? Well, that's a perfectly good question. And I just told you about perfectly interacting world volume theory involving supergravity, highly nonlinear, everybody here knows Einstein theory. So why isn't Newton complaining that his apple doesn't fall? Well, the reason is Newton's irrelevant in these systems, the same way he's irrelevant in pure gravity, where the Einstein equations are arguably 0. There's a funny symmetry of that system. We call it trombone, which is still be written out like music of the West. So the trombone symmetry of pure Einstein theory actually means there's no meaning to Newton's constant in pure Einstein theory. And what's happening here is extension of supergravity is also trombone symmetry. And there's no meaning in the trombonic symmetric theories. Where does it come into play? So when you're trying to eat lunch, eat something else. Right, and then you have to couple to it. The Newton's constant, or kappa, the gravitational pull constant, square Newton's constant, comes on the right-hand side of these equations with t nu. No t nu, no meaning for Newton's constant. It is naturally self-interacting without a Newton constant. The same. Modulo worrying about delta functions and so forth, which give everybody a headache for 100 years, and maybe haven't talked about it. So, if you just take R mu equals 0, there's two equations and don't bother me about significant delta functions, please. You have no meaning for Newton's constant. The trombone symmetry is very important. It gives rise to a family of solutions. If you work with the delta functions, that family of solutions can follow that parameter, which is called what? Which works with mass. That's the origin source of mass for pure Einstein. You have the same structure. Okay, so only if you try to add other sources, in this case, meaning other super multiples, do you run into this issue of vanishing Newton's constant. So you can play whatever you want, and you have as much fun as you want within the purest of gravity. But you can't couple it to anything else because the Newton's constant is going to vanish. So that's another sense in which this is not a full inventing of supergravity with all the things that it likes to interact with. It's just the purest of gravity. So that's type 1. Okay. There's another taxonomy. This Holland example reveals that there's something else you can do. It depends upon the boundary conditions that track the fluctuations as you come close to the world body. So study these fluctuations by separation of variables, please. We'll let the gravitational field be called traditionally h nu. Separated into a world volume part h nu of x, and a transverse wave function c. Again, we're trying to be lazy here and get rid of all these angles. Coming from 10 down to 4, 6 directions. There's one radius and a whole bunch of angles. Let's please look at this solution. Okay. Most of these vector angles are genuinely compact, so for them, I'll take a stand. I could have kept them, but then everything becomes much more horrible to it. So we're just going to try to boil it down to the essentials here. So we just here take the transverse wave function only on this radius, and then study the fluctuation system here in the separation of variables. Now, one of the not funny things is that studying spin 2 is the easiest thing to do, because you need to have all the indices on h nu of x, and the transverse part is only a scalar c, and you get involved in studying problems of a scalar equation for the transverse part of the wave function. And here you have a scalar Laplacian in the transverse embedding space with a warp factor. What comes out here is this quantity delta is important, involving the second derivative of the radius, and 2 over attached to rho comes up, and etc. So this is going to be the key part. So you split up the solutions in this way, and if you get a solution to this transverse problem, say with a 0 eigenvalue, it's going to give the h nu massless excitation in gravity. Okay, so this is what you do. You expand the general transverse wave function of x's and rho's, first of all, in this way, into a mode expansion, anticipating that there may be discrete modes as well. Okay, so there's a sum over discrete modes and an integral over the continuum modes, because it's an infinite transverse space. You are certainly anticipating a continuum of transverse wave functions, and that's related to this Holland-Warner problem. The effect of the transverse wave functions giving rise to the continuum, giving rise to a vanishing Newton's. But we're going to deal with that here, because if there's a discrete mode, that's going to cure the problem. Okay, so we have to study the eigenvalue problem of the transverse equation. It involves that quantity delta. With eigenvalues, I wrote it as minus omega squared, and the masses of the world volume excitations are going to be G with this parameter of the Solomon theory that comes up in the background solution. It was an interacting constant in the Solomon explanations. Okay, so now we have to study this problem here. So one thing we do is we first Schrodinger-ize it E, we make a change of variables, square root of sinh 2 rho. And then the relevant equation that you're studying, the eigenvalue equation here looks like a Schrodinger equation, a time-independent Schrodinger equation, with a certain potential given here. People who are very well educated, I guess, sort of thing that, in the great days of Russian physics, everybody immediately recognizes this sort of thing. Integral models. It's like, we know that, actually. Or rather, special color. So let's talk about it a little bit. The potential asymptotes to value 1 for large radius rho. And then that limit, the Schrodinger equation becomes like this. Notice omega squared minus 1. There's something special that happens for omega squared greater than or less than 1. So for omega squared greater than 1, you get traditional scattering state solutions, which are going to be delta function normalizable for large rho, as anticipated. That's your continuum. But for omega squared less than 1, you can say, oh, there you can anticipate maybe that you might find normalized constants. Maybe you don't look at the possible boundary. And recalling the rho dependence measure, we find that for large rho, if you demand L2 normalizability, you select out of the two solutions that you always have for second order differential equation, you select them Pauling behavior infinity, and it is normalized. Now, for omega squared less than 1, if you find it, you will then have a mass gap between this discrete mode and then continuum. And that will give rise to the localization. In particular, what's most attractive, of course, is to have a discrete mode at 0 eigentime, which means that the corresponding world volume excitations are going to be mass less than the alternative is one. And what's even nicer is that the Schrodinger equation for omega equals 0 can be solved exactly. So with Chris Erickson and student can sleep with Lagrange shit. Other books of the mathematical physics, right, under his pillow, he can actually get it sort of non-zero. But I was able to find this to get rid of all of his program on that night. Not so good with the zero ones, but fraction really necessary. Anyway, with this ceremony, the deep for 2 square root of 3 over 5 is properly normalized. It is normalizable and denormalized. Then you have massless H-negative fluctuations around the background, corresponding to massive 4-dimensional gravity. So this is the other taxonomy. So let's see, how can we really convince ourselves that this looks like a lower dimensional gravity? These boundaries. Well, look at traditionally the difference between far field and near field. I don't know what your TV transmitter talking about Shanghai, but you know that if you go near any antenna farm and you look at the behavior of the electromagnetic field, it's a mess. But you go a couple miles away, you might seriously 100% oh, this generation probably doesn't remember terrestrial transmission. Everybody thinks that TV signal come out of cable. Well, they used to have these things called antennas. And for those old people old enough to remember antenna, you know that you have to get far away from an antenna in order to see a nice big signal. So we look at the near field versus far field behavior. And so we look at the gravitational wave function, which involves the zero mode part. And there's one. The nice thing about this system, there's one discrete eigenmode. This is the system found by Fisher and Teller. That is the teller of the H bar. Before we let that here, the woman named Fisher. Anyway, the result of that integrable structure, we have a zero mode, and we have a continuum. And so you get these two types of contributions to the green function. Notice starting integral and 1 to infinity for the continuum part. So now the near field behavior. This is where you need Chris Erickson, right in the rigid outcome underneath this pillow, work out the corresponding sum. Because as you come near field, the entire spectrum, including the continuum, plays a role. And you see, it sort of knits itself together. R is the radius to your antenna farm on the rho volume. Rho is the transverse radius. So actually, G squared R squared plus rho squared is like a radius in a higher dimension, and you notice the power squared to the 3 cube. Oh, wait a minute, what I see one over R cube, 6 dimensions. It is revealing a higher dimension structure as you get close. Why 6? I was trying to be lazy and only include an extra radius in the transit direction. But I meant to talk about these angles. And of these angles, well, and there's one, so a bunch of extra coordinates, right? Just to sort of boil it down to something simple to write down in slides. Some of them are naturally compact, right? Spheres. But there's one which we call chi. Chi is actually the partner of rho. Remember, in QGC2024, it's structured. It's a non-singular space and it has a nose. Right, as you get down to rho zero radius on QGC2024, it becomes R2 cross S2, four-dimensional solution. And that R2 has a radius and an associated angle. It's a naturally flat R2. So actually, I'm allowed to talk about estimated solutions, but in looking at the Newtonian potential, it's actually going to remember that it's part of two-dimensional space. So we've got 2 extra dimensions in this simplified sort of estimated structure. That's why 4 plus 2 equals 6. That's why you get 1 over R cubed solution as you come to the nose. On the other hand, if you go far, far away, the green function has a different limit. It involves, first of all, C0, terminal parts, and, well, because of the mass cap, they're exponentially suppressed corrections, and they fall off. And that's a 1 over. So you have a transition from 1 over R behavior to a large distance, 1 over R behavior to a small distance. The experimentalists here used to be digging holes in green heights to see if they can see detections from Wisconsin. Right? Actually, they got much more sophisticated about looking at cavendish type problems, and that is an area of active experimental physics. In particular, in Vietnam, where people are really good at this sort of thing, where they are down to the order of 10 microns. They're doing the experimental geometries and it's Casimir effects, fantastic experimental technology. This is a topic where if you want to see the existence of extra dimensions, you can look for the deviations in Newton's law. Do you start to see a different power behavior? Okay, so that's the near field versus far field distinction. You see, this really is a natural concentration of gravity revealing itself for this distinction between near field, where you start to see the whole higher dimensional space-time, and far field, where it behaves like a lower dimensions. Okay, in fact, I'm coming close to the end of my talk here. That was the first example, and it has this nice mass gap. What we've done more recently, in particular with Rahim, is to look for other examples of this. So we have a little family of them behaving in analogous ways, but not exactly the same. They don't. In fact, the other ones don't have the mass gap, but still we get a concentration right. And you will, people in the supergravity community say, actually, we did something like this from random something already, which doesn't have a mass gap, but does have a similar probability in gravity. And that is, of course, fits. That's one thing to know. Then we also have various D3 branes on the result chemicals and so forth from various sorts. And then we found some situations where it is not concentrated, which is just simple D3 brane, although this does admit a consistent reduction at start. And some reduction does. It doesn't know how to do this concentration. What you have to do is examine the thermodynamic system. Remember, I strongly the converse problem. And then you have to go back and either study it Bushel or Teller, study the entire spectrum of the system and learn how to do integrals over the transverse wave functions. That's sort of thing Chris Erickson is very good at. Or you learn some more formal material about singular thermodynamic problems. And this is actually a type of mathematics. It started by Henry Weil in glory days of quantum mechanics, and has been developed more recently by mathematicians, particularly a mathematician called Zettel, whose book we discovered in the Dustin back shelves of computer college. Very useful. So by studying the character of zero versus infinity, you have to, in order to get also normalized wave functions, and there's an appropriate whole branch of mathematics we'll talk about it today. So you can sit to understand that's the way we understood it. Oh, by the way, these cases here involve a certain differential equation to solve the transfer thing. It doesn't have a name yet. We'll try to give it a R name, but then we have to write a descending chapters direction in the you don't yet put our name on it because this is where the solutions are not explicitly known. Boy, so people who are good at numerical relativity maybe can move this. But we can see that they are going to concentrate even without a mass gap. What happens is the corrections, remember in Salam Sepien, the corrections for the far field were exponentially suppressed because of the mass gap. What happens in these situations without a mass gap, which already one saw in the syndrome, is you have power law correction. You have the one of huge type corrections that you start, but not exponentially suppressed. You see, one over R cubed is still there out of large distances, but it's all off that over R, but still localization gravity. Okay, so that's my overview. Basically, there are two types of systems. Some special system. You have to talk about the hand on the full family, but we see there is a family of these systems. That the book and so forth, all of them by analysis of the boundary conditions that we need to satisfy. You have consistent reductions of one type of tax, one type of boundary condition. That's what I talked about first. All the programming, but on the worldwide problem of column one, or if you want to add any other ball, which you're going to run into vanishing Newton's constant. So you can only play within your supergravity. Any proportion for gravity is a nice secret. You want to do things just in the proportion for gravity, you can have a lot of problems. Oh, by the way, this you'll probably want us to talk about the real world. Maybe you probably won't. But alternatively, you can have fully localized lower dimensional gravitational behavior. This requires a normalizable transfer function like C0. And that requires a specific modified choice of near grain boundary conditions. So Robin is a French mathematician. Make it a specific for it. And then I've said it, this fits into the classification of singular self-adjoint terminal problem initially. And that's what I wanted to do. So thank you.
Yes, you're not caring about the future background or the position.
I'm not, well, yeah, can I stay? Can I add a couple, yeah, can I have these similar reductions in cosmological? Yeah, can. We were using on these lateral volumes, but also we can certainly have variable volumes in the cosmological. You see, and the answer is yes. However, you're tiptoeing into contentious topic in a whole string and supergravity theory. You mentioned deep, so you have the word anti, that to be more voluminous, because the whole issue of deep center vacuum in supergravity is a contention. And this small planning program and so forth saying how it's hard to do, and there are other proposals. Invention without data. Another approach, if you only say evidence, then you have encyclopedias and such solutions. This is a big problem. What Brandon and Sandra was going to do is very simple. They have anti-consider space in by dimension, and they take a knife, slice it. First thing they did was just write it in something important, so that's the value sign that we holding about. And they get what well done. But there are other slices they can make with leaving consider you know, and consider. So there's random and some and so forth. So one can, we were looking at solutions to rather than sort of by hand, dividing. Whether random something is a natural brain solution or not is something that we discussed over now. The favorite Shanghai liquor meetings, where as opposed to coffee in the morning. I consider all brain solutions here, 2 brains, 5 minutes, and so forth, but naturally, the intrinsic solution of the supergravity theory. This is a cutting it by putting it up. That's what I have to say, what is really that is given rise to an awful lot of discussion. But these ones, the D3 brains and so forth, and so on, they are natural brains. In a sense that the form fields of the supergravity, you're saying, oh, look, you have one form, the Maxwell theory. What is it like to couple? Now, bring forth the problem. Right? In Maxwell, result the roll line of the particle. Obvious that you're going to have a Maxwell theory, you'll have particle conditions. And then you can worry about the form of the delta. If you have a 3 form, illustrate 2 form gauge field, you say, oh, it likes to couple to a 2-dimensional world line. Oh, that's called straight. So you see there are natural line solutions that occur to the gravity theories, and the 11 dimensions of the gravity for the 4-form field theory, 3-form gauge field, 2-braid solution. Right? Remember, solution. So they're really natural solutions to the problem. So anyway, now you want to do that with the cosmological constant, you have to find it.
Other questions?
Okay.
That very natural thing on the side you mentioned the supersymmetric and not supersymmetric black holes.
Yeah.
And when it comes to your starting point is that you put only possible to have non.
Well, there's a distinction between symmetries of the theory and symmetries of solutions. Okay, now, what do I, the question I turn it around, not what do I see by non-symmetry? Standard black hole of Einstein Maxwell theory. Fortunately, black hole has a lot of community in there, is a non-supersymmetric solution. Does that theory have a supersymmetric solution? Yes. The external Risser-Nordstrom solution is the supersymmetric one. So the supersymmetric solutions are a special subclass of the generic family of brains. Right? So this distinction with symmetry of the solution, killing vectors, killing centers, and so on, as opposed to symmetry theory. Just because it occurs in a supersymmetric theory doesn't mean a solution is supersymmetric itself. But you know, it's
Okay, it's second again, Professor David.
All right. Decouple myself from my. Here, you get all 3 microphones apparently. And you get a transmitter.
Yeah.
And I'm supposed to get away from you.
Hello, everyone. I'm very happy to be here and make a presentation at such a nice conference in front of many people working in similar topic as I work on. And I'll present my recent work done in collaboration with Alexei Koshelev, the organizer of this brilliant meeting, about non-perturbative quantum gravity implications for the problem of singularities in the center of the black holes. So this talk will be mostly about the life of the action of four-dimensional non-perturbative gravity, which has a general form starting from quadratic and curvature terms. It can be written like this, and according to the results, several results obtained, in particular by Alexei Koshelev in recent year, several years ago. This action is the only action which affects two-point function of graviton. So graviton propagator is determined only by this action, and actually by two of these terms if we are working in 4 dimensions, because one of these combinations becomes proportional to the topological term. If we, of course, if we are speaking only about two-point function of graviton, quadratic action for graviton. So the extra terms, whatever the form is, they describe interactions of gravitons and they don't contribute to propagator. So if we concentrate on properties of graviton propagator, that's the only action which should be written and should be studied here. So, and we considered it, what happens with the black hole background itself, black hole solution, in statically, spherically symmetric metric. What happens with it if we go from if we extend GR to some non-perturbative gravity Lagrangian. By this Lagrangian, I actually can merge different concepts because it can appear as a 3-level Lagrangian in infinite derivative gravity. It can also appear as a non-perturbative effective action, for example, in a functional renormalization group approach, or it can be a compact way of writing a lot of contributions to scattering amplitudes in the general covariant form. So this corresponds to several approaches to non-perturbative gravity. As I mentioned, there are no other contributions to graviton propagator apart from this Lagrangian. Yeah, and let me also mention that this one is defined on top of the flat space to avoid further questions. Functions here are unknown parameters, but they must obey some consistency requirements. I will implement no ghost requirements, which means that the propagator must have no poles and also no zeros, because there will be also scattering amplitudes, and zeros in propagator will lead to some sudden poles which are not so good to have, and they will break causality. Also, I want to the desired thing is to require unitarity of the scattering amplitudes, not only absence of unitarity, not only in the sense of absence of ghosts, but also unitarity in the sense of having unitary partial wave unitarity for all scattering amplitudes. This is quite a strong requirement, but it's also something that we actually want to have. Absence of causality violation, which will be implemented such that we are dealing with the functions which are analytic in the whole complex plane. Even non-perturbative action allows to have only branch cut along one of the directions, only logarithmic branch cut, but all the rest of the propagator must have no poles, no other branch cuts, no other singularities, maybe except for essential singularity at infinity. That's our causality requirement. So then if we have some gravity theory, how can we compute these form factors, and how do we know them? In principle, there are several approaches which can be implemented, how this action will appear. It can appear as a field by means of many field redefinitions and perturbative quantum gravity and the EFT of gravity. So this section is not something very much new. If you take effective action of gravity, you can make many field redefinitions and bring it back to the propagator-like form. But in addition, of course, you will have many interactions. Then it's your choice which definition of fields you prefer, whether it's GR plus curvature corrections, or it can be partially written in this form. Another approach is which I have to mention, and there were brilliant talks by Benjamin Noor and Alessia Platania on that asymptotic safety program, functional renormalization group approach, where from RG running of several limited number of terms, one can obtain also one can write it also in the form of non-perturbative effective action, which means just the object from which we can extract any amplitudes, taking just three-level computation out of this Lagrangian. That's the definition of non-perturbative action for gravity, not only for gravity, but in general, non-perturbative quantum action. And there are methods which allow to obtain at least the candidates to more or less good non-perturbative action, where the results coming from functional renormalization group can be also written in this form. Then, in principle, this form of graviton propagator and graviton scattering amplitudes can be reconstructed from unitarity and analyticity requirements. This is like a bootstrap program, but I cannot say that in four-dimensional gravity, it's not people didn't go very far, because it's extremely complicated for some reason, especially in 4 dimensions, because of graviton pole and some extra divergences coming there. So the standard methods don't work so far. Also, I have to mention analytic infinite derivative gravity, where this form is a three-level Lagrangian. There was a very nice description of all the program and the results in talks by Gianluca Calcagni and Leonardo Modesta. So far, only power counting renormalizability is a kind of solid result here, but of course the non-perturbative version of the action, like renormalized action in infinite derivative gravity, is not yet known. We are dealing with a three-level action. So later on, for accessing the problem of whether Schwarzschild solution can remain in this action, in the theory with this action, I'll start from the approach in like analytic infinite derivative gravity, because it is at least possible to do it in this framework. So that will be my starting point. These functions now are all entire functions of the Lambertian, and they can be expressed as sums of Taylor series of the Lambertian. Then with this expression, a tremendous amount of work was done also by Titabir Biswas, Conroy, and Alexei Koshelov, and Anupam Mazumdar in order to derive Einstein equations following from this section. So already the first variation brings to some result which in short writing, it requires about 1 page, but trace of Einstein equation can be written quite a compact way, but still it's rather complicated. So this result was obtained by just taking variation of this section without any approximations, with taking functions to be a series of the Lambertian operator. And it contains some double summations, some nonlinear terms, and it's basically very long. So the problem of substituting Schwarzschild solution to this equation is very complicated. However, the result one can claim the simple result that if we take Schwarzschild metric outside the point r equal to 0, outside singularity, it gives zero curvature and zero scalar curvature and zero Ricci tensor. Due to that, we can say that Schwarzschild goes through equations of motion without Wald square term. But with Wald square term, it will not be the case, first of all. And I have to mention that from mathematical point of view, it's a bit, there is a trouble of having it as a solution even without Wald square term. So our approach is to simplify this problem by means of, so our purpose is to take the Schwarzschild metric, define it in some proper way and substitute it to equations of motion here, and adjust matter which will provide this kind of metric and check that this matter is not something crazy. In order to do it, we instead take a space-time integral of this equation of motion. So it's like the quantity which doesn't depend on the choice of coordinates, because I take an integral like with respect to space-time with root minus g, and its trace of energy momentum tensor is a scalar, which is important. Then I can choose like static coordinates of Schwarzschild metric and write everything in terms of just one integral. So this term leads to kind of, it's a standard GR term which corresponds to black hole mass. And this is the energy of matter which we require to make this equation hold. And due to the fact that we can omit total derivatives in this expression, we have a great simplification of trace of energy, integrated trace of energy momentum tensor. And this helps us to write down it in a very compact form where we have derivatives. So suddenly we got derivatives of form factors appearing in this trace of energy momentum tensor. So why we expect a problem also without Wald square term? The reason is that very roughly speaking, if we do not want to exclude the point r equal to 0 from the space-time and want to just see carefully from mathematical point of view what's happening there, and actually since we are dealing with infinite number of derivatives, it's better to do so, because with finite number of derivatives, one match just a few derivatives, but here we need to have sort of stronger requirements of analyticity. This means that since we have some quadratic terms here, we have to take a square very formally. We have to take square of delta function, which is just a simple infinity. So we might expect problems also in this case. So that's why we are not substituting. In order to study what's happening there, we are taking not Schwarzschild metric, but regularized Schwarzschild metric instead, and then take a limit. And since in terms of taking a limit of some function, it's we can more rigorously study what's going on in this case. So our approach is to take some regularization of Schwarzschild metric, which is suitable for infinite derivative theory, which means that all invariants, including invariants with 10, 20, 1,000 number of derivatives, all of them must be regular at r equal to 0. This cannot be achieved in any polynomial regularization. This can be achieved only if we take a sort of exponential regularization here, and when parameter alpha goes to 0, we recover Schwarzschild metric. But we checked all like curvature invariants with many derivatives, and we see the pattern that all of them are regular, and there is no sign why they will be not regular, because there is an exponential function here. So there is a smooth limit, alpha going to 0, which recovers Schwarzschild metric here. Then we can, the choice of this regularization is like the simplest one, which allows us to get some analytic results and do some resummation after all. So we did very straightforward thing. We took this metric and using exact and also checking it with Maple, substituted it to the equation of motion here, to this equation of motion. So we just make a straightforward computation, which is simply not possible to do by hand, but up to 10 derivatives, up to 11 derivatives. We found how coefficients of form factor, how coefficients in the expansion of form factors enter to expression for energy, for the trace of energy momentum tensor. We found that we are getting expansion in terms of like what we would expect to be black hole mass, several powers there, and we found that terms which are responsible for two-point function of graviton on a flat space, like propagator-like terms, they contribute to m² term only, and this term will take into account contribution from 3-point functions of graviton, and m²4 term will take into account 4-point functions of graviton, and so on. So in order to get some to make this result solid, we have to assume that contribution here from extra higher curvature terms, which we haven't written here, but there will be also more terms. We have to assume that contribution from these terms is less than contribution coming from quadratic terms. That's our assumption behind our analysis. Yes, cubic in the curvature with some random form factors there. Well, not very random, but in general, we expect in non-perturbative quantum action, we expect these terms too. No, not in bare action, but in like final action. Because in the bare action, there was Paul renormalizability clearly. There is no exact resummation. There is some approximate pattern for coefficients here, which we found. And so we found asymptotics of this beta and gamma terms, and I'll show plots for a bit later. So let me just comment on that first. Since in order to access the question about Schwarzschild limit of this metric, I need to take alpha being alpha going to 0. But all these powers are actually negative, which means that I'm getting infinity here, like naively speaking. But apparently this is not the case, because what can happen, these series are alternating, and in principle, it's very much possible that we get this kind of thing. For example, if we take exponent of -1 over alpha, which is perfectly going to 0, when alpha goes to 0, and expand it in terms of powers of 1 over alpha, we get also some series which are naively, they should lead to infinity, but apparently they are just resummed to 0. So we hope for similar thing will happen. And in principle, we can study when this thing can happen and when we can even can resum this series. The problem is that if these beta coefficients, they blow up very quickly with n. And in order to compensate this growth, Fn coefficients, which are determined by action here, they have to be suppressed for large n. Then in this case, series can be resummed, and this result will go to 0. But that's something which happens not always. I mean, it depends on particular form of form factors. The behavior of Fn as a function of n. And here, in order to have a good limit of this and have a good resummation, the requirement is that this series has to be must have infinite radius of convergence, because otherwise we cannot find out what's happening when alpha goes to 0. So it's a series, it's a kind of series in terms of 1 over alpha, and we need alpha going to 0 limit, which means that we need the infinite radius of convergence of this series. And knowing the coefficients, of course, we can find out what is the radius of convergence. Yeah, let me just show what we are obtaining for these coefficients. Like first 4 coefficients are more or less fine, but later they are getting longer and longer. Finally, studying them, just making plots and adjusting asymptotics, we found that they can be approximated as this kind of gamma function for large value of p. So it's a gamma function of 3/2n multiplied by some p-dependent gamma function. So they blow up as almost factorial squared, and it's very quick growth. And for small p, yeah, we are taking different values of p to check whether we are getting regularization independent results. So for these coefficients behave, for small values of p, their behavior is a little bit different, but again, they very quickly grow. And if these coefficients are just like 1 over n factorial, like it would be exponent of box, for example, then the series will be certainly divergent. They will not have finite radius of convergence. They won't have required infinite radius of convergence. Moreover, series which are expected in infinite derivative gravity with Tomboulis-like functions, the ones which behave like power law along real axis, they are even worse because they are of exponential type, which I'll show a bit later. And for them, the situation is even worse, and we cannot resum this series, from which we basically conclude that there are problems to have a singular solution in this kind of series. So if we cannot resum series, apparently we're having the fact that in order to reproduce Schwarzschild metric, we need some object with infinite mass, which is something that doesn't look like a black hole at all. And so if we restrict ourselves to finite mass objects, we just don't have such solutions. So let me show our explicit results, how it looks like. So what we've done, we simply did adjusting the asymptotic, computing numerically these coefficients beta. We were adjusting asymptotics for large p and small p just by guessing, looking at the plots, how these coefficients behave. So this is clear that coefficient, the fraction between coefficient beta and its asymptotics is something converging to some small, relatively small number. So the leading asymptotics written here seem to be correct. And for large p, it should be like more and more tending to gamma function of 3n over 2. Yeah. Well, it depends. I mean, these coefficients are combined. Finally, they will be combined with expansion coefficients of form factors of gravity. Then it depends. I mean, the main our statement is that many things here depend on the form of functions or the form of graviton propagator finally, and its series expansion. So my answer would be it depends on what is the graviton, what is the non-perturbative graviton propagator. better salaries. So that's the asymptotics for small p. We also may make an adjustment and check that it's happening here. So it has gamma function, some exponent, and some maybe polynomial like subleading asymptotics. And we will also make several plots for different values of p, and this thing depends on p. So we also see that some results will be regularization dependent, and so far we don't know precise interpretation of that. But some results we obtain are regularization independent. So regarding suppression of cubic terms in M cube, if we are taking 3-point interaction of gravitons coming out of only quadratic and curvature terms, we notice that these M cube terms coming from the action we study, they are not exactly suppressed, but they don't influence the result very much, because series which are appearing in front of M cube have the same or better convergence than series appearing in front of M squared. So the worst is series in front of M squared, which is determined by graviton propagator. Then we also noticed some possible cancellations, which apparently there is something special happening if we make an adjustment if the coefficient in front of y equal to -3 coefficient of in front of r term, but this corresponds to adjustment which is needed if we require no scalar degree of freedom appearing. We have some mild cancellation which means that convergence is a little bit better if this adjustment is made, but this doesn't affect the leading asymptotics of these terms. It's just some polynomial-like improvement. So the leading factorials, they are still there, and the coefficients are still blowing up very quickly. So let me formulate, let me formulate the result in terms of classification for possible graviton propagator. And also let me recall some mathematical results, like convergence radius of the series can be very easily obtained from series coefficients through Cauchy-Hadamard theorem. The relevant quantity for the question about convergence of the series apparently is whether the graviton propagator, what is the maximal growth rate of graviton propagator in the complex plane, not only along the real and maybe Euclidean directions, but in the whole complex plane, because it affects the behavior of series of coefficients of its series expansion. So maximal growth rate can be found from first of all, entire functions are classified by their order and type, and order can be obtained like this. Type can be obtained through the limit, again, through the limit of coefficients. Since we have all these coefficients at hand, we can just obtain these quantities. And order and type tell us what is the maximal growth rate of entire function on the whole complex plane. And here, S is an order, and rho is, S is type, and rho is order in this expression. So this is this exponent to the power S, Z to power rho. And there are a few plots how they look like. If it's a function of finite type and order, then it looks like it has exponentially growing directions in the complex plane. And then, of course, it depends on what power is here. How does it look like? Sometimes rho is not obligatory an integer number. It can be a fractional number. Even in this case, the function is still entire, but its asymptotic is it can have any power here. Moreover, there are very funny zero-order entire functions which behave sub-exponentially, and one of the examples examples is sum of series exponent of minus n squared z to power n, and it behaves like exponent of log squared. Apparently, this is the class of functions which should correspond to propagators in a local theory, like resummed propagators in the local theory or localizable theory, because it will be something behaving sub-exponentially. Interestingly, in this case, we can resum the series which I mentioned in the last slide. So due to this exponent, this kind of exponential suppression can easily kill this blowing up coefficients. So if I add the exponent of minus n squared, then my coefficients, then I'm getting finally resummed result, resummed to 0, because I can get the infinite radius of convergence of the series immediately. But this looks like the case for zero order entire functions, which we can identify with potentially what we should obtain in a class of local series if they are consistent. In the middle, there are exponential type functions which have some growth direction, and of course they correspond to non-local series. The propagators about which we like to talk in the sense of renormalizable infinite derivative gravity, these are the propagators having polynomial behavior in certain directions, but it's not possible to make them behaving polynomially or even exponentially in other directions. This is just complex plot from Mathematica to show what's happening, how crazy it looks like if you plot it like as a whole one. But this corresponds to limit of stellar gravity for physical directions. It means that it's just quadratic gravity with coefficients tending to constants. If we take momenta going along only real and Euclidean direction. So,
Box.
Hmm?
What's related in box, not box.
1/4 helps here. There is 1/4, which exactly choice of box squared is to have this picture, because if just box, then you don't have it along real and Euclidean direction. And this is exponent of this kind of sigma behaves exactly like box, like extra box, which makes propagator behaving like 1 over k to 4. But I just achieve it in a ghost-free way by somewhat crazy function. But I mean, here I'm just showing that I can achieve it. But it's known that this kind of function has exponential of exponential type. So it blows up like exponent of exponent, and there is no chance to get finite resummation of the series I mentioned. That's the case.
Yes.
Yes, because Taylor coefficients of exponent, they are not like they don't fall down quickly enough to compensate the growth factors coming from all these nonlinear terms. Okay, so how much time I have? Okay, I'm close to the end. Main result is that singularities, the question of singularities in non-perturbative gravity is connected to maximal growth rate of function standing for the propagator, for the non-perturbative propagator, I would say. I've been speaking about Taylor series, but non-perturbative propagator has a branch cut. But I'll comment on this a bit later. In principle, this classification is also valid for functions having logarithmic singularities, because these logarithmic singularities is along real axis, but all crazy stuff happens along other directions where this singularity is not important. So this can be also applied to non-perturbative propagator. the result is that for zero-order entire functions, singular solutions are possible. If for exponential functions growing slower than exponent of 3/2 of z to the power 3/2, conversions depend on regularization, and we are uncertain what's happening there. So we notice that the equation of conversions depend on the parameter p in our regularization. There is no clear answer what's happening there. But if the function is growing faster than exponent of z to 3/2, or like faster than exponential, singularity is not allowed, because we are getting infinite mass of black hole in this limit. So let me make a very brief comment about how I propose to go from tree level to non-perturbative action, and what's the modification if we go from starting from entire functions to allowing logarithmic singularities in non-perturbative action. There are several requirements of analyticity for non-perturbative propagator. Apparently, since we allow the non-perturbative propagator to be a function of to be an analytic function everywhere except one branch cut, this is a very strong requirement fixing the form of how the propagator should look like. I can transforming this branch cut into infinite circle by means of changing variable z to log minus k squared. I'm getting something which on z plane must be an entire function. Moreover, it must be not just entire function, but exponent of entire function, because it should not have poles and zeros. For this reason, the propagator should be entire function of logarithm of minus k squared, but such entire function which have no poles and zeros. And that's for this reason we can get a quite crazy looking form of the but very generic form of the propagator, that it's exponent of entire function of logarithm of k squared. That's what is required by analyticity for non-perturbative graviton propagator, the very generic form. This kind of form, if the function is growing fast enough along if its maximal growth rate is fast enough, it can be approximated by entire function. Because its logarithmic behavior is not very important, but this statement can be shown mathematically. So when going from trees to loops, we expect that non-perturbative propagator will be written in this form, but its UV asymptotics, its maximal growth direction will be determined by some entire function, which means that the previous analysis, which was done for entire functions actually, should be also valid in non-perturbative action for gravity. But there is a big problem, which big issue, which I need to mention, which is the fact that we actually don't know how tree-level propagator affects the non-perturbative propagator. So there is it is not clear how to obtain what kind of form will the propagator have after non-perturbative resummation along these crazy directions, whether it will become smooth or not. It is extremely complicated, and unfortunately, any perturbation theory is not working here. Perturbation theory can be applied along real axis, but it doesn't give an information about the other directions, which are sensitive to such fine effects like singularities. So apparently, I have to mention that in infinite derivatives of gravity, there is a very complicated open problem on how to resum and what is the form of graviton propagator and also scattering amplitudes further in the resummed action, in the non-perturbative action, where the bare action is the one like it is studied in infinite derivative gravity in a renormalizable formulation of it. Maybe it will become smooth, and this is a plot which I did for the result obtained by functional renormalization group in the paper by Fehre, Littim, and others. This one is looks like much more smooth function, but again, it's a question to obtain what is the exact UV asymptotics of this function, and how the question of singularities can be resolved there. So that's a few open problems which I had to mention. And for conclusions, I have to say that there are many different proposals for formulation of non-perturbative gravity, but for the graviton two-point function, all of the proposals converge to the same action with two independent form factors. And basically, the unitarity, the absence of scalar degree of freedom even fixes one form factor in this section. For this reason, it might be very useful to write the action in the form of quadratic action with form factors, because it's everything which it includes all the contributions in this form which affect two-point function of graviton. So substitution of Schwarzschild metric is a quite non-trivial computation, and in our work we made a suggestion to approach it by taking exponentially regularized metric first and then getting a limit afterwards. And this seems to be kind of a solid mathematical approach, and we have managed to obtain a quite interesting result that a Schwarzschild metric limit may not exist, and it doesn't exist for infinite derivative gravity with polynomial propagator along real and Euclidean directions. The one which is of the mostly interesting from the point of view of having renormalizable setup for infinite derivative gravity. Not all effective actions for gravity are compatible with singular black holes, and this might be not a problem, but the opposite, it might be a resolution of singularity problem if gravity has such an action that it doesn't admit singular solutions. And we formulate precise criteria for non-perturbative propagator, which relate its maximal growth rate on the complex plane with the existence of singular spherically symmetric solution.
Yeah, I have one question and two comments. The question is how do your results change if you switch off the Riemann-Riemann term? Because in that case, Schwarzschild is an exact solution of the theory, and I'm wondering how your analysis would change if you set the Riemann-Riemann to 0.
Yeah, sure.
This is the question.
Yeah, I understand. As I mentioned, Schwarzschild is an exact solution everywhere except for r equal to 0. And we really intended to take carefully this limit. And we found that it doesn't, there is nothing special nothing special is happening if we switch off Weyl squared term. That's the result of what we noticed. I don't know how to interpret it, but apparently it seems that even if
No, I mean,
Can I stop this discussion? Because
yeah, maybe it can be a long discussion indeed.
Okay, let's first ask. Okay, first.
My experience with these kinds of systems go back to Weiss and Mueller in 1950, who looked at hierarchical correction to scalar systems in particular, and then looked at infinite systems also. And there are lots of interesting questions that arise out of it, like the structure of the light phone connected to unitarity and causality. So you have this sort of fuzzy light phone structure that evolves. Have you looked at those aspects, particularly causality?
You mean causality aspects?
LIFO is not sharp.
Yes, for causality, the argument would be that in principle, this theory can be, you can make a field redefinition in such a way that the propagator will be local, but all non-locality will come to vertices. Then causality can be studied for example, like I did it in my work with Claudia Daram and other colleagues from Imperial. We checked the absence or presence of time advance in the theory, time advance of the propagation of the signal. And the expectation is that, again, if we if we define causality as absence of resolvable time advance, then there is a lot of space for theories which should still be. So there could be non-local theories in this domain where causality defined in this way is still preserved. But that's a question which I plan to study in the future someday. In my opinion, the proper setup is to check explicitly the time advance and time delay after rescaling all this non-locality to vertices and do this analysis. Why I have a hope that causality should be still there is that according to our experience with like study of causality for some EFT, we noticed that there is basically we compared positivity bounds, which are strictly based on locality of the theory, where locality is explicitly assumed. And we found that domain allowed by causality is larger than domain allowed by locality and causality. So there is a hope that there is a place for non-local theories. And that's also one of the questions I'm studying now.
Okay.
Look at the various papers on causality. Macro causality is preserved, there is no Shapiro kind of stuff. Micro is the right.
Yeah.
For those actions that do not meet a singular black hole, have you checked if there is a solution that can mimic the observed black holes?
Well, we didn't go so far with finding certain solutions, but there should be certainly compact objects. Maybe with at least this ansatz which we used, it's a metric with either just compact object or two horizon object with two horizons, inner and outer. And in principle, maybe for some theories it can go through and. But we haven't yet checked it.
Okay, it will be late, and let's turn on again, and we have.
No, Is where these three microphones.
Yes. There's another clip on, right? Yes.
So these I have to put it here, no?
Yeah. So these two are more in for streaming services. So let's put.
Okay, so this one as well. Not this, oh. This one?
Yeah. This is what the local.
Jesus Christ, how many
Three.
meters?
And you can hold this receiver, so put in your pocket. This is 0 pointer. This is a pointer, and this will move your slides.
Okay.
Lower direction.
Okay. Mariam Mufmadi Lopez, don't worry. Don't worry about that. How much time do I have? 35 minutes?
35, total 40 maybe.
I try to stick the time because we are already late.
The next session, where we have a talk by Mariam Papanetas from the University. We talk about scaling up the university and time of similarities.
Thank you. So my pleasure to be here, and thank you to Alexei for the invitation. Alexei, Sravan and us, we met in Covilhã, small town in Portugal, where we had a wonderful time. Well, my talk will be related to the talk we heard yesterday, the last one by Manu. So it's about the late time acceleration of the universe and how in some cases there might be some singularities, okay? And that would be on the second part of my talk, I will essentially see how those singularity could be removed within a quantum approach. So let me introduce. So we know that our universe is homogeneous and isotropic on large scale. So essentially a cosmological principle that Manos was telling us yesterday. And we essentially know only 4% of the matter contents of our universe. The rest is unknown and is dubbed with a dark adjective. So it's a dark matter and also dark energy or some modified theory of gravity like the one we heard yesterday, F of Q, F of R, and so forth. Now, why do we know that our universe is currently accelerating? So as Manos told us yesterday, so essentially this is coming from measurement of supernova. So supernova looks to us much fainter than they should if we don't have that component on the matter content, okay? And then those observation has been backed up by measurement of the Hubble rate at different redshifts, by measurement of the gamma ray burst. So essentially we have some distant measurements that trace the expansion of the universe from given redshift to now. Also backed up by baryon-acoustic oscillation, the CMB, the large-scale structure through the matter pulse spectrum and the growth function. And there are, of course, some tension in our cosmological model nowadays, those we heard yesterday. So H0, so essentially the measurements that are coming from higher redshift, like the CMB, gives an H0, which is smaller than the one that are coming from local measurement, like the supernova, and also some tension on sigma 8. So the way in which we deduce the clustering at higher redshift is different from the measurement that we go at lower redshifts. Now, what we know is that for sure the equation of states that is describing our late time acceleration or late time inflationary era has an equation of states which is pretty much close to -1, as Manos was explaining to us yesterday. So there are essentially two ways. So either we modify the right-hand side of Einstein equation, so we invoke some energy, new energy components, or then we have to modify gravity on large scale. So Manos' talk was essentially about these parts. I will focus on this one, okay? So how can we describe the late time acceleration of the universe? Simply by modifying the right-hand side equation of Einstein theory. So some basic theory, so Ricciardo equation is telling us if we want this to be positive, then we need to include something here, such that this sum here would be negative, and if it dominates over this one, then with this one minus, we'll have this is positive. Okay, and there are many ways of doing it. And in addition, observations are telling us that the ratio between this pressure and this energy density is of the order of -1. Okay, so the simplest case would be lambda CDM, so just a cosmological constant, or we could have W called dark matter, which means a dark energy component with a constant equation of states. Okay, so that's simple things. Now, if we want to describe the background evolution, one way of doing it is by using a cosmographic approach, and in particular by using some expansion introduced by Starobinsky, Sahni, and collaborators. So it was a very smart way of doing things, such as if you are in lambda CDM and you have just a cosmological constant called dark matter, this coefficient will give always 1. Okay, so the jerk or S3 would give 1. And then the other one would be the lurk and the snap. They renormalize them in such a way that they would give again 1. On this plot, what we see is S4, S5 versus S3. In this case, it doesn't give 1 because we include as well radiation. So in the past, what happened is that, of course, dark energy is not important. So the 3 components will be, the 3 kind of model that we have here, an equation of state slightly smaller than -1, equal -1, and larger than -1. In the past would be we get the same thing, this line and this line. Now, as we approach today, this 3 model could be different. Nowadays, we can go for measurement up to the jerk, okay, not further. So we don't have a precise measurement for S4 or S5. These are the background level. So what happened at the perturbative level? So at the perturbative level, if we go to we use the Newtonian gauge, and we decompose the perturbations that usually. And for example, here we plot essentially what happened for this mode. So it's a mode that entered recently the horizon. Nowadays, the horizon would be 10 to -4, 10 to -5 megaparsec -1. So the perturbation, again, it will depend on the kind of model we have. So W could be larger than smaller than -1, the red line, -1 exactly, cosmological constant or quintessence, W constants are larger than -1. So the gravitational potential, again, in the past would be essentially the same. This is what is shown here. The present will be D0. Okay, the 0 because it's the log of A respect to the current value nowadays. And depending on the kind of model, so if it's lambda CDM, the perturbation on the gravitational sector goes to 0. If it's quintessence, it will approach a constant. But if it's phantom, which is essentially an equation state smaller than -1, then at some point in the future, this can change its sign. And this what is telling us essentially that at some point in the future, the structure will be ripped apart. Okay, so in fact, for W constant smaller than -1, what we have is a big rip. And the scale in which this will happen would depend essentially on this case. So the smaller is K, the sooner this happens. Okay, so larger scale would be the first to be destroyed and so forth until the smallest one. For delta M, there isn't much change from one model to the other. If we want to compare it for lambda CDM is what we have here. And dark energy perturbation, so if it's lambda CDM, of course, no perturbation on lambda. If it's quintessence, so it would be, phantom, it would be this red one, and for quintessence, this one. For F sigma 8, so the same thing that can be done, and there isn't much change between the 3. Of course, we are plotting for an equation state that's changed slightly from -1. So let me say a few things about these phantom models. Okay, so these are models in which the equation of state is smaller than -1, okay? And that can be, although favorite observation, it can be problematic from a theoretical point of view. Why? Because they violate some null energy, some energy condition. So essentially the weak energy condition is violated because this term, and the null energy condition, because these can be negative, although the energy density, of course, is positive, okay? And the strong energy condition is also not fulfilled, but that's not strange. This happened already during the inflationary era, okay? And one way of modeling this kind of phantom model is by parameterizing the deviation with respect to a cosmological constant by a power rho to some power alpha. And here I will just focus on this value for the following reason. And the first one, so if alpha is 1, so essentially what we have is a constant equation of states. And if its W is smaller than -1, we would have a big rip in the future, which means essentially that a finite cosmic time, some quantities will blow up that I will describe in a moment. Now, if alpha is 1/2. This is the equation of state that we'll have, and we'll have a big rip sent to our infinite cosmic time. That's what is named as a little rip. And then if alpha is 0, so the deviation with respect to a cosmological constant is by a constant A, where A is positive, then we would have is a little signal of the big rip. So essentially, the Hubble rate blows up at an infinite cosmic time, but the time derivative does not blows up. Okay. And yeah, for a recent review on this topic, so there is this review by Nojiri, Odins of Iconom and Pan. And okay, and this side over here, what I'm saying is that if you map it to a phantom scalar field, that would be the type of potential you would have. Yes. An equation state smaller than -1. W smaller than -1.
So is it from P to W?
W is the ratio between P and, yeah.
So with W less than that.
Sometimes you can have it in other kind of scalar field, in which is, but the thing is that your W effective had to be smaller than -1. That's the definition that I will take on my talk. Okay. So I will speak about 3 cases, the 3 that I mentioned before, which is the big rip, the little rip, and little signal of the big rip, because these are the only dark energy related singularity that take place if you have phantom, if and only if. This other one, the big rip, the sudden, you can have them even if you don't have phantom matter. So the big rip, as I said, is a cosmological singularity that happened at some finite cosmic time in the future when the curvature blows up. And it's also a singularity from the point of view of geodesic, because you cannot extend the geodesic beyond that point. These are the 2, the little rip and the little signal of the big rip. They are not true singularity because, first of all, from a cosmological point of view, the curvature blows up at an infinite cosmic time. Okay. And yeah, so the little rip is essentially a big rip sent to our infinite cosmic time, and the little signal of the big rip is something smooth. So the Hubble rate would blows up, but not its time derivative. So what are the observations telling us about those 3 models that I mentioned before? So this we did it only a few years ago. So we fit the background model using supernova, the CMB empire in acoustic oscillation H of Z. And the 3 models written in terms of the redshift are this one. So this would be for the big rip. E is H divided by H naught. Okay, the same thing here and the same thing here. So this would be a phantom quintessence model. This with beta positive would lead to a little rip. So when A gets very large, H or E blows up. And for the little signal of the big rip, the same thing happened. When A gets very large, H blows up because E is essentially H divided by H0. So after fitting the model, so what we can see is that W indeed can be smaller than -1 and a big rip can happen. Then for the little rip, the fitting that we got is that omega LR has to be relatively small, the order 10 to -2H, okay, 10 to -3. And then finally, for the little signal of the big rip, so again, this deviation encoded on this parameter related to the AH showed before has to be as well small. This from a background point of view. And the fitting, we can see it here. So the best fit between these 3 models would be the one corresponding to the big rip. So it's the one that gives the smallest reduced chi-square, then to be the little rip, and then finally the little signal of the big rip. Now for the perturbation, how do we deal with them? As I said, it's phantom, so we have to be careful when dealing the perturbation. Not only because it's phantom, because it's dark energy. So the CS square will be negative. So we have essentially 3 components. So we have radiation, dark matter, and dark energy. And we integrate from the radiation dominated epoch till nowadays. So instead of using some approximation as the one we saw in the last talk, here we use the full first order perturbation on GR. Okay. So the key point here when dealing with dark energy perturbation with the perfect fluid, one has to be careful because the adiabatic speed of sound, this one here, can be negative. So for example, simplest case is W smaller than, W negative. Your CS square here will be W is negative, and then can lead to some blows up of the perturbation. So what is usually done is to impose by hand, is a phenomenological approach by hand, and I insist on that, by including the speed of sound at the rest frame. And this one we take it positive, and in such a way that then for W called dark matter, we would have well-behaved perturbation. But as I insist, this is done by hand. Okay, it's a phenomenological approach. It's not coming from any fundamental argument. Usually CSD square is set to 1 because it's the value that you will get for the speed of sound for a minimally coupled scalar field, standard one, no fancy, okay? And that's what we did. So the first thing, we assumed this CSD square equal 1, and I will show later what happened if we change that value. Of course, and for the initial condition, those are imposed by the measurement that coming from inflation from the for AS and NS. Now, the initial condition that we impose is that initially the three components talk to each other, so they are adiabatic. So if we know the initial perturbation for radiation, those will fix those for matter and for dark energy. The same thing for the velocities, okay? At the perturbative level, the velocity will show, okay? Now, how do we fix this one initial, this delta initial? So essentially, this is coming from the primordial inflationary power spectrum. So we know that, well, in the radiation epoch, so the perturbation on the gravitational potential in the Newtonian gauge will be roughly of this amount, and this one is fixed by the inflationary area. So once we know this parameter, NS and AS, we know the initial value for each perturbation, which means for each K, okay? So that's what we did. And we choose by hand CS square equal 1. So for the matter sector, so there isn't much difference between the three models, so essentially the same thing. So the red one are the first to re-enter the horizon, this red one, so this means this one. And this one is the last to enter the horizon, which is this one over here, okay? And zero, redshift 0 is nowadays, like here, the same thing. You can see here that something strange happened on the gravitational potential, but I will show it later. The dark energy perturbation, so I've shown for the three model, the red one is the, let me remember. The red one is the big rip, the green one, the little rip, and this one, the little similar of the big rip. The initially you would see that these perturbations are different, and they are different because once we fit the model, okay, oops. We have initially, this value can change from model to model, okay? That's the reason why initially they are different. Okay, and this is what happened for this in this type of model in the sense that the structure are ripped apart, and the reason why this happened is because the perturbation, the gravitational perturbation will flip its sign at some point in the future. And this depends on the model, and also it depends on the scale. Okay? So the smaller is K, which means larger distance, the sooner this happens. These are the modes that entered before the horizon, and will be the last to exit, and those will be the one that will be ripped apart later. So what I mean is essentially so here we have the scales. So we'll have inflation, radiation, dark energy, and dark matter. So you have the mode that enter. Those that will exit some point in the future, the sooner, I mean, those are larger scale. Those that exit before, those will be the first to be ripped apart, while the other will be later. That is essentially what is shown on that plot. And for F sigma 8, so the fitting is the one shown here. Now, what happens if we change CS square, because it's a phenomenological model, so we can make it small, but not too small, because otherwise we will see some, I forgot the word in English, some clustering of dark energy, which is not observed, okay? So CS square cannot go too small. Now, well, this is just a zoom from the previous slide. So again, we can see here that the gravitational potential will flip its sign at some point. The smaller is CS square, the sooner this happens. And this is again a zoom of the previous slide. We could think about some interaction between dark energy and dark matter. Sorry, and at what time did they start? Should have checked it. 20 minutes. Oh, okay. So what happened is if there is interaction between dark matter and dark energy, so that the next thing we looked at was, so we assume this kind of interaction, a linear interaction, where this lambda, depending on the sign, it will essentially tell us if there is a transfer of energy from dark matter to dark energy or the other way around, okay? So when we do the fit, again, at the background level, so what happened is essentially that lambda, okay? Lambda, where is it here? Lambda is positive, is positive, is positive. And if we go back, this means essentially that there is a transfer of energy from the dark matter sector to the dark energy sector, which means if we had the big rip, we will keep having a big rip. But if we have a little rip or little similar of the big rip, because this lambda is positive, then instead of improving the situation, we would end up having a true singularity, okay? But these are the observations that is telling us if lambda is positive or not. And the best fit between the three models would be the one, let me see if I remember properly. Yeah, this one for the interacting with rip, then interacting with rip, and interacting with the signal of the big rip. And then this is the fit, essentially. Okay, on all these models, so there is some blows up of the curvature, either at a sooner time or a later time. Recently, with some colleagues in Spain and also in Poland, we have been looking at some models which are asymptotically de Sitter, so W approach -1 from below, and they give a very good fit, even in comparison with lambda CDM. So that's just small publicity about one of our recent work. Now, can we get this from a more fundamental point of view? And I will show two examples, and I try to go as quick as possible. One possibility is by invoking a three form, and that was something we did some years ago with Sravan and other collaborators there in QVilia. So what is a three form? So essentially it's an antisymmetric tensor. And if we are in 4 dimensions, so we have 4 possibilities: a scalar field, which is a 0 form, a vector field, P1 form, P2 is another possibility. And the one that I will be speaking about is this one, the 3 form. And why the 3 form? Because it's the next simplest thing that you can have after a scalar field. And in addition, as they can, in a natural way, induce some phantom-like behavior, although the action is, I mean, it has the standard kinetic term. So what happened, why they have been popular in the past? Because essentially, if you have no potential, or even if V is constant, this naturally leads to a cosmological constant. And it was used back in the past as a way of tackling the cosmological problem, the cosmological constant problem. Because that's one of the reasons why people got interested in it. Then it has been analyzed in the context of inflation and also on dark energy. And here I will briefly mention something about it on the dark energy sector. So it has only 1 degree of freedom. Once we assume some this Friedmann-Lemaitre-Robinson-Walker geometry, then the only component that will not vanish are the special components. If we were dealing with black hole physics or wormhole, as we did in another work, so it will be different. It will be the one that depends on T that would survive. Okay, so chi, this field chi, will encode essentially the physics induced by this 3 form. So the Friedmann equation, if we have only 3 form, would be this one. And you can see that there is an extra term if we compare it with the scalar field case, this 3h chi. Okay, the Raychaudhuri equation is this one here. And you can see that whenever this term here is negative, which means essentially that the potential is the decreasing function of chi-square, then we can have a phantom behavior. Okay, and that's the reason why I got interested in this kind of model. In order to have some intuition about what is going on, so we can essentially write the equation of motion as if it was minimally coupled scalar with some effective potential. So this is what is done here. So by looking at this term, that could be the partial derivative of V respect to some kind, some V effective, okay? And you will have the standard critical point for a given potential plus another critical point, okay? These 2 critical points. These 2 critical points, once we choose a potential, which is a decrease in function of chi square leads to a little rip of the little sigma, okay? Which is the second case over here. So this is the potential, the Gaussian potential, okay? Now, and this green line with some, could be some shifts, horizontal shifts, would be the V effective. So what happened, essentially, the three form, depending on its kinetic energy, it will end up here, okay? Or if it has enough kinetic energy, it will go slightly a bit up and then down, okay? We are currently with some colleague in National Taiwan University, and one of my students in Bilbao. We are fitting the current model, and these are some preliminary results where we can see the value more or less of H0, what would be, and sigma 8. And essentially, it seems that at least the tension on S8 could be, or sigma 8 could be released in this type of model. As I don't have much time, so I will skip this slide. And here, essentially, the comparison with lambda CDM. Yes, so this would be lambda CDM, and this would be the model we are analyzing. We have as well, because this can give some phantom-like behavior, 10 minutes, okay. We have as well got some solution, regular solution for black hole. This is from a phenomenological point of view. So the idea was essentially close to the horizon, we have Schwarzschild, then the three form is switched on, and then the singularity at r equals 0 can be removed. And we can get also some wormhole solution, okay? Let me move to another topic, and this is some work I did with Theodor Borislavov and Prado Martin Moruno from La Complutense. Borislavov is a student with us. He's about to finish now his PhD. And one of the things he did during his PhD was to analyze this kinetic gravity grading, some of the work of Alexei Bickman. So the idea was that they showed that they can have some phantom-like behavior on this model, which leads to some to solution that asymptotically de Sitter. And what we were analyzing was essentially to see, can we have some big rip solution on this type of model? Okay, so that's the question we addressed, and the answer is yes. So these are the Friedman equation, and this is the Raychaudhuri equation. Okay, and we assume the case in which there is a shift symmetry, so essentially K depend only on X, and X is the kinetic term, and J depend only on X, and X again is the kinetic term. So we did the dynamical system analysis, and because we were looking for solution corresponding to a big rip, so then we had this H, the Hubble rate, we had to compactify it, and we did it in this way. This small h, when it approaches 1, this h blows up, and that might highlight the presence of a big bang or a big rip singularity. Okay. And for the dynamical system, so essentially this is the way in which it can be written. The prime stands for derivative respect to the log of A, okay, or X. Now, there are two things I would like to highlight here, C1 and C2. So if C1 is positive, then, is positive, then the effective equation of state coming from H dot will be negative, okay? Will be smaller than -1. On the other hand, if C2 is positive, this means that the scalar field would have an equation of state which is phantom, okay? So there are two different things. One thing is to have H dot positive. Another thing is to have an equation of state for the scalar, for matter, which is phantom. So we got the fixed point, and indeed there is one of the solution. So this is when we switch off the function K, and J has this is a power of beta, then there is a big rip solution on when beta is between -1/2 and -1/4. Here I mentioned just one of the cases. The other cases, you can have a look at them on the paper. So essentially, we would start in a radiation-dominated epoch, then we will lead to a matter-dominated epoch, which is a saddle point, 2 days, and then finally, we end up on the big rip. And this would be the evolution, essentially, of the background model. Fortunately, we were not very smart in choosing the function, because when we analyzed the perturbation for our choice, it's not a problem of the model, it was our choice. We had essentially either a tachyonic or a ghost. So when we didn't have a ghost, we had the tachyonic instability, and the other way around. How much time do you have left? 5. Okay, so I have 5 minutes for the last part. So far I mentioned that, well, some model of dark energy, which the observation are pointed to one, that there are some available model, could lead to some future singularity, okay? So this means that quantum effects, maybe they are not only at the Big Bang, small scales, but we could have them also on large scale, okay? And this is the issue I will discuss on these last minutes. So I will do it on the context of the Wheeler-DeWitt equation, because it's the approach that I know. Okay, here we have heard plenty of approaches, and I wish I knew as many approaches as the one that we discuss here to apply to these kind of theories. Okay, so the Wheeler-DeWitt equation, as I guess most of you know, is essentially the equivalent to Schrödinger equation once we invoke GR. This approach was to analyzing future singularity, dark energy singularity, was started by Klaus Kiefer and collaborators. So the first work was done by Mariusz Dabrowski, Klaus Kiefer, and a former student of Klaus, Barbara Sandhofer. Then it was analyzed by the Big Break, which is a kind of sudden singularity, by Klaus and Alexei Kamenshik and Barbara. And then we joined them on this approach, and we analyze it for other singularities, which are sudden singularities. For example, the Big Demarrage is a sudden singularity, the Big Freeze is another type of singularity. And we did it not only within GR, but also in some modified theory of gravity. And for a more general review, not too long, we have this work with Klaus and Prado Martinero. Okay. So briefly, I will show two cases. One in which we have truly a phantom scalar field, which means essentially we have a minus here. And then I will show another example for the 3 form where we don't have a minus here. Now, because it's phantom, is like if you have this potential the other way around. So instead of going down, the scalar field would go up. And this is done for the little signal of the Big Rip. So essentially for this type of potential is a quadratic potential. Okay. The Wheeler-DeWitt equation in this case will have a plus here instead of a minus that we will have if we have a minimally coupled scalar field, which is standard. And in general, we cannot solve this equation analytically. So we need to impose some approximation. And the usual approximation that we use is Born-Oppenheimer approximation. And it can be shown, it's some lengthy calculation, but it can be shown that there are always solutions in which the wave function would vanish, and that could be interpreted as a singularity avoidance, or in this case, an abrupt events avoidance. So let me move to the case of 3 form quickly. So this is essentially the A with 3 indices I showed before. We had that everything was encoded under chi, and now it would be, instead of chi, we will use phi. Why? Because with chi, we can diagonalize the Lagrangian, and the Wheeler-DeWitt equation would be much simpler. So this is the Hamiltonian. Once you have your Lagrangian, you can define your momentum for the geometrical part and the matter part. And once you have that, you essentially you define your mini superspace metric, and then by choosing the Laplace-Beltrami operator, so we end up with this Wheeler-DeWitt equation. Please notice the sign is minus. The one we had before was plus. So with the 3 form, we'll have the same sign that we will have for a standard Miller-coupled scalar field. Yes, with the right sign. Again, we use the Gaussian potential because it's the one that leads to the little signal of the Big Rip. I'm finishing. I'm just. And after some lengthy calculation, easy but lengthy, so it can be shown again that we have a wave function that when we approach this little signal of the Big Rip, the wave function vanish, and therefore we can say that there is an avoidance of that abrupt event. Okay. Now, similar thing, we did it within modified theory of gravity, in particular within F of R. So the Wheeler-DeWitt F of R theories was, as far as I remember, first deduced by Vilenkin. And well, for the F of R, we use essentially his approach. In that case, it was for de Sitter. If you have this type of theory, so you will have F of R where there is R to some power. And then we extend also we got the Wheeler-DeWitt equation on ABI type of theories. Okay, those are Palatini type of theories. And let me leave you here with the conclusion. So I start discussing this phantom dark energy model, which could describe the latent acceleration of the universe, first from a phenomenological point of view, and then how we could get them from some fundamental field, also for the model of the three forms. So the reason what we are analyzing is not only for doing the fitting, but also to see if we can release the sigma 8 tension. It seems the sigma 8 tension can be released with some model. H0 is not clear. And then quickly I describe what we have done with Klaus and Klaus Kief and other people in the context of dark energy, latent singularity, and the will do it. So Shishir, thank you. That's it. Okay, H0. The last data. So that was essentially what yesterday Manu Saridakis was telling us. So essentially the H0, you can have those that coming from supernova, it has a larger value of H0, and those from the same be a smaller value.
This I know.
Yes.
I asked you the last update. Okay, I'm not interested in what Adam Rees say.
Yes.
Because beside of Adam Rees, there is Carnegie. Okay, supernova project, which is not in agreement with Adam
Yes.
Rees, as
Yes.
you know very well.
Yes.
And you know that 1.2
Yeah.
systematic plus statistic, which Adam Rees is given,
Yes.
has nothing to do with reality.
Okay. So I don't have an answer to your question. Okay. What I mean, I'm a phenomenologist. I mean, they give me the data, and then we look for a solution from a theoretical point of view. I don't have, no, I don't believe in any. I mean, I give the data. I mean, I take the data and I see which one fits better, the model that I analyze. But it's not a matter of belief. The data are there.
It's data, I told you, yeah.
Yeah.
Because what Adam Rees is saying doesn't make too much sense.
Okay.
There is Carnegie project where they measure, calibrate supernova.
Yes.
Just in two different bands. I forgot already how it's called. In one band they get 71 plus
Yes.
minus 0.85 plus minus 1.2 systematic, in the other 73 plus minus the same story. So already tells you that systematic cannot be less than 2. And nobody knows what is systematic about, because you are not sure that systematic is distributed according to Gauss. Therefore, the statement like there is 5 sigma disagreement or tension, which is made, don't make any sense.
Okay, I didn't mention any sigma tension. I said that it's only in one of my slides I was referring to these.
So you are
What I'm trying is to see if there is some model in which we can have W smaller than -1, and the perturbation are well behaved, and there is some kind of maybe singularities in the future. So that's what I try to convey on this talk. Okay?
yeah,
No, I'm not an experimentalist. I would lie if I'd say I'm an experimentalist.
There's a conflict between this Adam Rees measurement and the plan. So
and again, which calibrations they use? Based on CPEs or red dye?
I don't know. I guess if you ask
There is a conference next week in Krakow, and this is led by a team, a European team they are essentially working on this, on H0 tension.
You mean this?
No. Look, it's a cost action. That's what I was referring to.
There is 2 projects, which Americans, Carnegie. There is project on web. I do not know, because actually they were supposed to be taking some data last year, but it was on technical, there was technical breaks for this James Webb telescope. And of course, the question is very questionable, because to speak about 5 sigma or whatsoever doesn't make any sense.
Yeah.
There is very good review paper on this subject in JCAP by Wendy Friedman, Who said, okay, so take this thing, then it's 5 sigma. If you take this thing, then there is 2 sigma. If you take the other thing, then there is quad sigma or even less.
Yes.
So it's not simple questions.
Yeah. It's not a settled. And were you here at the talk of yesterday of Manus? The last one? Because his talk was precisely about the H0. The last one.
It's not about that. 2 weeks ago, we were at the conference with Reese and Friedman and other people. We asked, is this attention or not? We couldn't get a straight answer.
From whom? From Reese?
No, from Reese, of course, there is. From Wendy and from other people, it wasn't clear.
No, she said, okay, she always is polite person, essential people. Okay, but she was not insistent with the research.
Yes, exactly. Only Reese was really insistent.
Yes, just to respond to the discussion for lunchtime, now.
Can I just say one last thing? Those of you that work more from a theoretical point of view, so if there is, for the case of model that I showed that there is a big rip, a little rip, if you think there is another way of tackling the singularities without using the Wheeler-DeWitt equation, I will be quite happy to discuss with you. But sorry if I interrupt.
Okay. So what should we do this? And what should we do with this? Right, it's a clip. Okay.
This is for the local.
Okay. So what?
Here you can be the fire.
Let's see if it mark as yours. Yeah. Let's put these things on. So this is the example and it will get you forward.
Okay.
Down direction.
Uh-huh.
And this is the light.
Okay. Okay. Perfect.
Principal 40 minutes, but I guess people will be grateful if you finish the time.
Okay, I will try. So it's my great pleasure to be here in Shanghai, even though the temperature is maybe a bit too crazy. So I will try to entertain you before you get completely hungry by talking about some mystic subject, namely about how to make GOS stable again. Okay, so actually this work is based on why again, because we first stabilized GOS in this paper together with Cedric Defaye and Shinji Mukayama. So we basically killed all runaways and we provided an analytic explicit proof that some systems with GOS can be manifestly stable and stable in all possible senses, by the way. And then we made it stable again together with, again, Cedric, Shinji, and then Aaron Held also joined us. And this was published in this anniversary special issue of JCAP. And you see, it's kind of funny because this conference is very appropriate for it because, in fact, it's one of the most ghost-hunted conferences I ever attended. So there were so many people talking about ghosts, like at least these talks were partially dedicated to ghosts. And I think it's very appropriate to mention them and how one can make them stable. Okay, so you see, in this audience, I probably do not need to repeat that, but there is this living with ghosts, and because it's a conference on quantum gravity, I should say that Hawking and Hertog were writing already there that perturbation theory for gravity in dimensions greater than 2, of course it was known before them, requires higher derivatives in the free action. Higher derivatives seem to lead to ghosts. And then they say states with negative norm. And actually this approach was mentioned in many talks, in particular in your talk. And actually, it's not that kind of living with ghosts which I'm trying to explain you. So I'm not going to change any standard rules of quantum mechanics. I'm going to live with ghosts as normal states with normal standard product in Hilbert space. Okay, so my definition of ghosts, which I'm going to use, is that ghosts are dynamical degrees of freedom with negative mass. Okay, not imaginary mass like tachyons, but negative mass. And if you want, these are systems with kinetic energy which is unbounded from below. And then, you know, in this audience, it's probably not very appropriate, but you could say, okay, why should they care? Because for most people, it's immediately pathological, and they don't care. But let me quote not only Hawking and Hertek, but another colleague of us who actually wanted to come here, but he could not come. And what he said just less than a month ago, that there is no way to live with ghosts and no way to live without ghosts. I think it's maybe a bit too pathetic, but whatever. He could not come at the end to this conference to enjoy all these ghosty talks before. Okay, so let me give you some interesting lists, maybe because it's such a ghost-hunted conference, you know, to review what are different interests with ghosts. So first of all, it's kind of interesting cosmology, even though some people would say that it's pathological cosmology, but maybe after Miriam, I should not discuss it more. But actually, okay, so this phantom dark energy or super accelerated universe with growing Hubble parameter, it's not excluded by data. Some people would even say it is slightly preferred by data, but it's completely statistically insignificant. But clearly, even if the true result is W equal to -1, the data will be always just close to -1 and will also allow you to have W slightly less than -1 if you don't put a prior, right? Then you could have bouncing universe if you allow for growing Hubble, and you can also have inflation with blue spectrum of gravity waves and many other interesting things in cosmology. And what is, I think, interesting here for this conference, so this bouncing cosmology can be ideologically very important because it's a question whether you hit a regime of quantum gravity in the past. So if you don't allow for classical bounces, then you do need to hit this regime. If you allow for bouncing cosmology, maybe you don't need quantum gravity in the past at all. Okay, then another thing is related more to ideology. So high derivative systems have ghosts due to Ostrogradsky theorem. So it's a question of general dynamics. Should we care about systems with high derivatives or not? And then, you know, another funny thing is that actually systems with high derivatives are even used in technology. So random number generators, so-called QR circuit, does use third order equations, okay? Because that's the lowest number of dimensions in which you can have chaos. So in reality, you know, people use this third order, what is called jerk equations, to generate chaos. And the question, why not to see them in nature? And then, of course, in presence of Kelly, I should not remind that, you know, there is a normalizable gravity model with high derivatives. And other questions are related to entropy and thermodynamics, because, you know, if you allow to your energy to be unbounded from below, then it's kind of interesting how to understand normal thermodynamics. Even more interesting is the following question is how to screen gravity, right? Because the real cornerstone of our technological civilization is our ability to screen electromagnetic forces, okay? So if you're able to screen gravitational forces, a lot of things would be possible, right? So to screen gravity, you would need to violate knowledge condition, or if you want to have ghosts, okay? And to be able to control them. And then this is also deeply related to cosmological constant, which we don't know how to estimate, because if you are able to screen gravity, you are also able to screen gravity from quantum fluctuations. And this would be very interesting to understand whether this tiny value of cosmological constant is somehow related to gravitational screening. Then, of course, it also would allow you to discuss all exotic compact objects like wormholes and so on. And last but not least, because you can continue this list, you can also study, let's say, massive gravity, and you see that there are always ghosts. And even in this ghost-free massive gravity, as we know, if you put this ghost-free massive gravity on cosmology, it has actually two ghosts, okay? So therefore, it's not ghost-free. So therefore, it's interesting, what does this all mean, right? Because, for example, you can kill Boulevard Desert ghosts, but the price for it, then you get two other ghosts, okay? out of your 5 degrees of freedom. So it's kind of, you can continue these motivations. There are a lot of interesting problems. And, you know, because it's such a diverse, so to say, subject, let's be more simple and let's try to understand it first in mechanics. Okay, so for mechanics, this guy is, if you want, our foundational pillar, except of Newton. Maybe you know this guy because he's an Italian. Who knows this guy, by the way? Who would recognize him? No, but you're Italian, Fabio. Of course, he is Giuseppe Ludovico, right? So, okay, good. So if you recognize him, then, you know, you would probably know that the notion of global stability is very often attributed to him, and it's called Lagrange stability. And it's actually a very simple statement. It's a statement that the motion is finite, or if you want, bounded in phase space. And I'm going to prove you, especially that's for Sasha, because Sasha is going to leave. I'm going to prove that there are systems with Gauss where we can analytically prove global stability. Namely, I start by whatever initial data, and my system remains in a finite region of phase space, okay? Which I can actually estimate where. And the interesting thing is, this is, if you want, if you imply global stability, there is no runaway, okay? So a system does not escape to infinity. Finite time, infinite time, doesn't matter. So it stays bounded. Why it's interesting? Because that implies that if you use quantum mechanics and you keep in mind, let's say, many world understanding of quantum mechanics, in that case, by distribution of initial data and evolving classically from each initial data, you will never run away. So therefore, it will be normal, well-defined quantum mechanics because the system is bounded in phase space. And then if you don't recognize this guy, you probably don't recognize this guy neither. Who knows who is this guy? Fabio, any chance? Okay, so this guy is Lyapunov, and Lyapunov has another notion of stability, namely the one which is more used currently. And this notion is the following, that if you start from a given solution close enough, you will stay close enough. And most importantly is that this you can choose how close you want to stay, and for each closeness you can find appropriately close initial data. Okay? And most importantly, this happens forever. Okay? So basically, you specify me how close you want to be, I give you how close you need to be initially. Okay? So what I'm going to show is that both notions of stability can be realized in simple mechanical systems. Okay, now this I will probably almost skip because that was already mentioned. So there is a Ostrogradski theorem. You know, basically this sign is important. That's your Gauss. This is Ostrogradski. Of course, Ostrogradski would become crazy if he knew that one could talk about this using this language. But he was writing it all in this article, which is very fresh, very modern, you know, just 1848, I think, or 46. And as a true Russian, he was writing everything in French. And what is more interesting, of course, he didn't care about neither Gauss nor any instability. He was deriving their Hamiltonian mechanics because he couldn't read in English and he was not aware of the works of Hamilton. But he was a mathematician and therefore he studied most general case. Okay, so what is most important for us is the following, that if you take, let's say, second derivative system, so which depends on acceleration, in that case, you introduce momenta like what he prescribed, and there are two momenta, and then there is this Hamiltonian, which is linear in this P1. And one can understand why it's linear in P1, because this P1 is related to third derivative. The third derivative was not there at the beginning, okay? And therefore, it can enter only linearly if you want. Okay, so this is a fundamental problem, because then if you look at this Hamiltonian, this P1 is linearly here, but nowhere else, okay? So therefore, I can choose my initial data so that this Hamiltonian is as negative as I want. And if I put it into interaction, this can be also the case. I can just move towards this negative value of the Hamiltonian. Okay, so now, basically, this is famous instability. Very, very quickly, you know, you can take, for example, this system. It's like, of course, this will not be necessarily unstable because it's quadratic. But just to give it feeling what it is. I start from normal oscillator plus acceleration squared. What I get is two guys mixed with the wrong sign, okay? And that's the origin. Why am I interested in wrong masses? Because here, in normal circumstances, there would be mass, and here it would be mass, and we see that here it's negative, okay? Good, so this is all well known, and if we go to field theory, you see this oscillator with mass here would be translated into modes, where if I take, let's say, cosmological perturbations, so instead of z squared, I use capital Z, then the Z translates exactly to the mass, okay? So therefore, if my Z is negative, that implies that the Hamiltonian for each mode looks like an oscillator with a negative mass, okay? Okay, very good. So now there are two types of instabilities that you all know, but that's not that relevant. Here, the only thing what I wanted to say is the following, that Gauss, you cannot see in linear analysis, okay? Even though some even very well-known people would claim, oh, we have done linear analysis, we have not seen any instabilities. This is completely irrelevant because from linear instabilities, you can only catch gradient instability. Gauss only appear due to interactions, okay? For example, if I look at this system, and this system is part of gravity, it is coupled through gravity, let's say 2 photons, then I can produce 2 photons and 2 of these, let's say, curvature perturbations if this was Gaussian, okay? And the rate for this process, if the couplings are just, let's say, gravitational, was calculated by Jim Klein. And you see, it's just an estimation, right? Because if you're in Lorentz symmetric setup, you would integrate over all momenta, and that would diverge. If you assume that even in high UV you break Lorentz, like what Andrei Barvinsky was telling us in Khajava-Lifshitz, then you would not care. You can introduce cutoff, and this would be just, in each vertex you put 1 over m Planck. The whole amplitude is in that case 1 over m Planck squared. Therefore, the rate is 1 over m Planck 4. And then you need just by dimensional reasons to put external momenta there, okay? So therefore, the rate per unit volume per unit time will be heavily dominated by your cutoff, okay? What is interesting, actually, in field theory, it's not necessary that it's really, really bad, because if you violate Lorentz, then this cutoff, okay, it's kind of low, but it's not necessary when, in contradiction with experiments. And that was abused by Jim Klein recently in his models of phantom, even dark matter. That's maybe a bit too extravagant. And, also it's very questionable how one can believe to such calculations. Okay, so basically major point is the following, that you can take normal matter, Gaussian matter is like scissors, but kind of funny scissors, because due to evolution, you can expect that they can open up, because the Gaussian matter can decrease energy, normal matter can increase energy, total energy remains constant. And you could think, okay, these scissors can open up indefinitely, right? Infinitely large. And that's would be runaway instability. However, the key point here is this nail, okay, which keeps them together. It's an interaction. And now the question is, can you make such an interaction that the scissors would not be opening up at all, okay? Just before we go to see such a possible nail, such a possible interaction, let me illustrate how unstable can it be in normal circumstances. Let's take normal oscillator. Let's couple it to Gaussian oscillator through normal quartic coupling. And then by some value of coupling constant, you see that the energy in the first guy will grow quite far, because this is logarithm, right? So, and this is kind of like a lab parametric resonance at the end, but it happens due to a negative sign here. If you actually decrease the coupling constant, suddenly, and you see this difference is not that big, I mean, it's factor 2 only, but suddenly the onset of this instability moves from, let's say, 10 periods of the first guy to 600 periods of the first guy, okay? It's because, in reality, this onset of this instability can be postponed very far away. And this is very important. Why? Because people were studying such systems numerically, and they were claiming, because you see, this instability is purely nonlinear, they were studying it numerically, and they were finding no instabilities. But of course, this is not necessarily so, because they could wait a bit longer, and they would discover this instability, okay? Very good. So therefore, we need analytic methods to understand whether some things are stable or not. So let me tell you what were our first model where we managed to show that there are some systems with negative masses or ghosts, which can be manifestly stable by very normal mechanics. And that would imply also normal quantum mechanics, by the way. Okay, so you take normal oscillator, ghosty oscillator, you introduce coupling between them, some potential. Let's say masses are 1. And then what happens is that what we wanted to have from some reasons is this is potential. Okay, it's not very, my favorite potential, but it's not that bad because it's just some coupling constant divided by a normal analytic function. Okay, nothing special. This square root is never 0, as you can see by this presentation. Yeah. You see, that's an interesting point. So we didn't want to change the sign in front of y squared because I want to disentangle tachyonic instabilities from ghosty instabilities. Because I want to avoid the situation when the system is linearly unstable from the very beginning. I want to disentangle these two effects. So therefore, see, if there were no interaction here, this system is just two oscillators. Both of them are stable, no problem at all. But that's a good point. Okay, so now what is interesting? So in this model, the interaction is quite specific. It's actually bounded. Okay, and moreover, the further in configuration space you go, the smaller is this potential. Okay, you kind of could think maybe that's the reason why this thing is stable, because of course the harmonic parts, x squared and y squared, they all grow in particular directions which you want, right? Okay. Now, okay, you can plot this potential by different values. So it turns out if absolute value of lambda is less than 1/2, it looks like kind of saddle. If lambda is larger than 1/2, there are two saddles. And then what's kind of interesting is that you can write this total potential expanded, let's say in this case, around 0. And what you see that there are two frequencies. And of course, due to interactions, these frequencies get a bit shifted. And one shift is positive, another one is negative. And you could say, okay, if my both frequencies are real, right? So omega squares are real, positive. In that case, maybe there is stability. But don't forget, this is all about interactions, right? So therefore, this linear analysis is not enough. It's not a proof. Okay. So actually, one can prove that here, both these saddles, either both here or this one, actually one can prove, and I will show you later, I'm saying it for Sasha because he's leaving, that they're, in both cases, actually Lyapunov stable. Okay, so basically they're as stable as people want, always. Okay. And one can show it using nonlinear methods. That's important. Good. So what is unusual is these are saddle points, and that I will show you that they're stable. And of course, because they're saddle points, they're fixed points. They're points of, so to say, equilibrium, right? Which is also a bit unusual. Okay, so I will more concentrate on this case because it's a bit simpler. So let me show you numerical solutions. It's very boring. Okay, it looks like some oscillations in x and y. Looks kind of stable, but okay, I showed you before that if you wait long enough, they may stop being stable. That's projection of phase space in px and y, py and y. So this is like kind of donut structure with kind of like oscillations there. And if you look at x and y, so-called analog of Lissajous figure, you see that it kind of covers such interesting pillow. Okay, you could expect maybe it's okay, but you don't know. Because you need not only numerics, but something else. Okay, but it's a hint that at least for a long time, this may be stable. Good. So now the question is, why am I claiming that it is stable? Okay, and there is some black magic, you know. And I took this picture actually in the castle of Albrecht von Wallenstein. So you see, and I suspect because for Albrecht von Wallenstein, his astrologist was Kepler, so I suspect it may be drawing of Kepler. But whatever. So it's some black magic, which I'm going to use. And namely, black magic is power of imagination. Okay. So what is power of imagination? In reality, I have taken this potential because of particular reason. Namely, because there is this guy E, which is our first integral. So the system is actually integrable. Okay. And this is what makes it very particular. And how have we guessed that it's integrable? By the way, there is no simple local symmetry which we could put there or guess what it is, because you see, this integral of motion is quite involved. This K is a generator of, let's say, hyperbolic rotations. Then there is, if you want, energy for the first guy, energy for the second guy, and then interaction multiplied with something. So it has some particular structure. Okay, so actually we guessed it because we were using the results of what we thought was Darboux, but turned out to be actually Liouville. And these are results which are 150, 170 years old, very fresh. And what we have done, of course, neither Darboux nor Liouville would be interested in systems with negative masses. But what one could do, one could make imaginary but canonical transformation and obtain a new system and check whether in subclass of the systems, everything remains real if we insist on imaginary parts. So why it's important? Because canonical transformations preserve Poisson brackets, so therefore everything what was conserved remained conserved. The only thing what happens, you switch the sign, okay? So now the point is the following. If you look at this first integral, again, it can be written in this form. And as I said, it's just generator of hyperbolic rotations and two energies summed up with positive sign, right? So now what you can see is that this guy is bounded between these two coupling constants, right? Positive, negative, and positive value. So then that implies that this integral of motion is always bounded between these two values, okay? That's from the structure of the theory. Why it's important? Because it applies this inequality at the beginning, okay? Then this integral of motion is larger than the sigma minus lambda and sigma plus lambda. At some later time, it's also bounded between new values of sigma, but same value of lambda, okay? But what is crucial that this E is the same. And therefore, you know that the sigma A minus absolute value of lambda should be less than sigma B plus absolute value of lambda. And vice versa, sigma B minus lambda is less than sigma A plus lambda. So therefore, what you established, that at every consequent moment of time, the sigma B is larger than sigma A minus 2 lambda and less than sigma A plus 2 lambda. The sigma A was just a bit larger than actually the radial vector squared, right, in the phase space. So therefore, what you have established that during infinite time, this system will stay in a bounded region in phase space. Okay? So that's analytic proof. So now one can also show this in a bit different way, because what happens? So what we just have showed, what is called global stability, okay? Arbitrary initial data, doesn't matter how far away or how close. By the way, also doesn't matter whether I have tachyonic instability or not, because I could start around 0 in the case lambda larger than 1/2, okay? Nevertheless, my motion will be happening, evolving up to infinite times in the bounded region of phase space. So now I can show you that the origin is stable by lambda less than 1/2. So I take this E, and actually I will show you that, okay, at the origin it's obviously 0. It's actually positive in this part of configuration space, and it's actually in the other parts, it's actually positive provided that these omegas are less, I mean, these lambdas are less than 1/2, okay? So basically, this fits the definition of Lyapunov function as Lyapunov showed in Kharkov in 1892. This corresponds to what is called second methods of stability, and that implies that this E is Lyapunov function and the system is Lyapunov stable, okay, in the origin. So basically, this shows you two standard notions of stability for Gaussian systems, manifestly, explicitly proven. Good. So now you can look at like some not very nice realizations through high derivatives, so just to mention that it's possible to rewrite it as kind of system with Q2 dot, but that's not that relevant. Another point is that, you know, you could say, oh, you got it through some analytic continuation, right? And therefore, who cares? We knew that properties we all love of weak rotation, right? That we knew that it's all stable, and before, why should it be unstable now? Let me show you some very simple example, because I am talking about global stability, which cares about whole phase space, right? So let's take normal p squared plus cosine hyperbolicus. That's your phase space. Of course, closed trajectories, nothing particular happening. Now I do complex transformation. This is canonical transformation. And what is not very often explained to students, that if you do canonical transformation and want to have completely equivalent dynamics, then you need to start from the same initial data, transformed, right? So, of course, had I started after this transformation, you know, where I would get this guy. Had I started now from complex initial data, I would not gain anything, right? But instead, you see this P bar, if I use it only imaginary, it would get the same dynamics. It would be just equivalent. However, here I use P bar to be real now. And of course, whole thing changes because this guy is cosine potential, and with cosine potential, this is the structure of my phase space. And of course, if I go here, I will just run indefinitely because I will be over barrier, right? So basically, this would not correspond to global stability at all. Okay, very good. So now let me tell you how we made Gauss stable again in a much nicer fashion, because of course you saw that this potential is a bit ugly and it's kind of very special, but it turns out that it doesn't need to be that special. So let's take this model, like positive kinetic term, negative kinetic term, potential. Then what we have is that potential parameterized by two free functions. So it's huge freedom, okay? Two free functions. And this u is given by that, where r is just the difference between x squared and y squared, you see? And u and v, if you want, these are what is called hyperbolic, or if you want, analytically continued elliptical coordinates, okay? So this is just the simplest way to write it, unfortunately, but whatever. For you, what's most important thing? Potential has two free functions, huge freedom. Okay, so now what are the simple conditions for stability? This constant c, which is there just purely for dimensional reasons, if you want, should be positive. And f and u are bounded from below, so f and g, sorry. And then what we want that at infinity, these functions, they grow faster than if you want squares of u and v. Okay, so if you satisfy that, and as you understand, it's very easy to satisfy that, taking this f and g arbitrary, then my claim is that the system is Lagrange stable. So the motion will be always bounded. And by the way, that implies that quantum mechanics will be good. So now what we have, so we can use, if you want, what is an analog of Dirichlet-Lagrange theorem, which is also similar to what Lyapunov was doing. And it's triviality that if you sit at the minimum of potential energy and your kinetic energy is positive definite, in that case, you just stay there, okay? Because you cannot get any energy out of anything to escape from there. Okay. So now what is an analog of this Lyapunov? That if you find some function, which is again, zero somewhere, grows outside and stays either constant or cannot increase, in that case, you are stable. So now let's see what's the analog. Again, the same black magic. There is this first integral. And this is the interesting structure of this first integral is the following. Again, this hyperbolic rotation guy, then sum of absolute values of kinetic energies multiplied with this c. So therefore, we want this c to be positive, because in that case, it's positive kinetic energy. And then there is this guy u, which has this structure. It should not care about the structure, but it looks like a potential. Okay, that's the most important thing. So now you could see that if it satisfies these conditions on G and F, then this U will create you a potential well, effectively. Because what we want to use this integral as an analog of energy. Because for Lyapunov proof or this Dirichlet, whatever, Lagrange theorem, it doesn't matter what you use, what kind of integral of motion. So therefore, you see, this is positive kinetic energy, and this potential, which we want to be smooth, right? So there's no singularities, and to grow at infinity. And this is, if you want, potential trap. So therefore, this Gauss will be trapped. Good. And then let me give you one example. You take just normal polynomial expansion of this guy, of this potential, take same constants in both U and in G and F. And let's say what we have proven, it's actually a super simple statement, that the lowest polynomial which you can use, so here n should be 4, and that implies that this potential is 60. Okay, so it's polynomial order 6. That's the lowest order at which your effective potential in your would-be energy, in your integral of motion, creates you this potential well. And why can you see it? Because you see this positive C's, this is normal harmonic part, this is some quartic part which is irrelevant, and the 60 part which grows, and you see C is positive and this C4 is positive, C4 was coefficient from here, then this is a potential trap. So therefore, if you stay there, you cannot escape. Okay, so now look, what one can finally do, one can plot this effective potential. Okay, it's some polynomial, so you can find minimum of this polynomial, and all minima would correspond to equilibrium points, or the points where you can see the vacuum, if you want, right? So depending on parameters, it can be either this shape or that shape, and what is interesting, so you can look at the ratio of this omega C and C4, and depending on that, you will have either this shape or that, you see? So now what you can immediately recognize is the following, that, I see. So that minima of U are, of course, saddle points of V. That's triviality because U is minima, you cannot escape, you need to stay there. It should be, of course, a fixed point. But fixed point, it cannot be minima of V, so therefore it's a saddle point. So we have some more formal proof of that. And what is also very interesting is that you see, you took two oscillators, you put them into interaction, you would expect that the whole system would create runaway or go astray. In reality, what you do, you created 4 new vacua. If you want, it's kind of spontaneous symmetry breaking. So you were staying around 0. That was okay. You put these guys into interactions. There are 4 new minima, and this minima corresponds to non-vanishing values of coordinates. Okay. So basically, and by the way, these configurations are more stable than the origin. That's another interesting story. Okay. So now this is just for illustration purposes. So this is how the motion would look like. Again, XY projection. You see the whole phase space, of course, is 4-dimensional. I cannot plot it. But in projections XY or PY, PX, this looks like this. Time grows, as you see, and this changes the color. And what is interesting, you could have a chaotic motion around 0, but nevertheless, it is bounded, so therefore it can create you all these nice pictures. But nevertheless, the motion is bounded. Okay, very good. So now you can say, okay, you found now polynomial interaction. And by the way, what's interesting, that implies that this interaction, contrary to the first model, grows. Okay, so they can interact very strongly and nevertheless be stable. That's important point. So now the point is the following, that there is Kolmogorov-Arnold-Moser theorem, and this theorem is stating you the following, that if you found some integrable system with finite motions, the motion happens on invariant tori, and if you introduce small structural perturbation into the system, these tori are getting deformed up to measure 0. So measure 0 solutions can be unstable. All other solutions are on this tori, and this tori are just getting deformed. So therefore, if I bring this system with interaction with anything else, and this interaction is not as strong as this polynomial, which can grow indefinitely, right? In that case, I will be fine. So you see, that's a proof that if I couple it to whatever, or if I change this polynomial, by the way, by a bit, nothing will happen. Very good. So then the major question would be, why have not we seen such systems in nature yet? Okay. And you know, I don't pretend why have not we seen this as quantum gravity or anything, but even in condensed matter. So what's wrong? So what's wrong is not stability, it's something else. And what would be very interesting to figure out. So thanks a lot for your attention.
Negative and complete quantization. Let's gravity and motivation. But is it really normalizable with this quantization class?
You can ask Kelly. Yes. You see, it's actually non-trivial because I can tell you what's kind of. It's only partially, I think, because you see, there's some symmetries which are not that trivial in the following sense. You see, it's like to have Killing vectors or Killing tensors. So here, it's more like a response to Killing tensor, not Killing vector. So basically, to figure out a true symmetry there, of course, infinitesimal symmetry is very easy to write. Just through Poisson brackets, you know the generators, and that's it. But to find globally, what do you need to do with these trajectories? It doesn't look that it's feasible, to be honest, because it's a heavily nonlinear system. And actually, what's also interesting, it has some kind of chaotic behavior. Well, and therefore, I don't think I can find this trajectory, so find this symmetry at all. That's a problem. Sure. Yeah, absolutely. Absolutely. Yeah. No, of course. But you see, this generator, after that, in order to find globally what the symmetry is globally there, I would need to integrate these equations. And that corresponds to integration of these equations, which I cannot do. Because, you know, of course, I can provide you, if you want, a generating function and be as integrable as, let's say, on Landau-Lifshitz, provide you, let's say, integrated action or whatever. But it doesn't help me to see trajectories and to basically have a visualization of the symmetry, unfortunately. But would be nice if it was that obvious. But regarding, look, for me, it's just one of the motivations to talk about this GOS. It's not, this is very far away from the.
You say that this quantization.
Yeah, of course, this would be very interesting. But you see, the problem is the following. So in quantum mechanics, it's okay. So we can do quantum mechanics with that. There wouldn't be a problem. But it's normal quantum mechanics. In normal quantum mechanics, it wouldn't be a problem because it's not a question of ordering there. By the way, that's another important thing. Because in this integral of motions, there is no ordering problem. So therefore, it will be preserved by quantum mechanics. So that's kind of easy to check. What will be in field theory? That's a different question. That I don't know. Right. Very good point. Actually, look, to give you a spoiler, we also do some numerical simulations for field theory, kind of motivated by such potentials. And you know, usually people claim, oh, there are all these like things will be completely unstable. Numerically, we don't see anything. Like we don't see any instabilities. But the problem with this numerics that you don't know for how long do you need to wait. Because even for simplest cases, there could be some instabilities with onset, which can be postponed actually exponentially. That is what is called Nekharoshev estimate, which is really not a very good good thing, not very good news. It's, if you want, it's kind of catastrophic event. If you really look at this estimation, it basically tells you the following. So if you want estimation of this, if you have many degrees of freedom, how would you departure from this invariant tori? And it happens that the amount of phase space, which is not on tori, grows, or more at some moment exponentially far away in non-analytic structure in coupling constant, so in e power 1 over coupling constant, you may start developing huge exponential, or a little bit stronger than exponential instabilities. But the interesting thing is for field theory, you see, that's an interesting story. For field theory, in most cases, one could prove, not for gravity, but for simple guys, you know, simple field theories, one can prove hyperbolicity. And if you believe in relation between this instability and normal quasi-classical systems, then you could use estimation wishes from this hyperbolicity, and that gives you bound and growth. And it can be very small. No, it's much harder to check. I mean, nobody knows how to do it. Yeah, of course. And also the question is to see if you start doing classical simulation on a computer, you always do finite number of degrees of freedom again. Which also, yeah. But the question is, how does it scale with increasing this number? But at least so far, we don't see anything numerically and classically, of course. It's symmetric. It's actually x to minus x, y to minus y symmetric. It's parity symmetric. Yeah, probably. But I'm not sure this is the real. You see, I could make slight modifications there, breaking this. Not even slight. I could introduce x cubed term, and it would be odd in parity. But because I care about behavior at infinity, this would not change the struct. Maybe I should show it like.
Context, it's a very big difference whether or not you preserve those parity.
Sure. Of course, I understand. But you see, the point is, if you go to this formula, you see, so here we have quartic. So you're right, it would preserve this ghost parity, the structure, if you want this guy. But I could easily introduce here a term which would be, let's say, my ghost was y cubed. And it would not change anything. No. Sure. But you see, we have even been doing these experiments because it's very easy to understand. Because, of course, then you are not, basically, if you want, by Kolmogorov, Arnold, Moser, these guys at infinity will be more dominant because they're 60. And y cube is smaller. But then you know that you go to infinity and this is a potential prop for it, and that's it. So you would not. So basically, it's not it's interesting, but not spoiling the system. Okay, thanks a lot. Yes. Let me see. Yeah, should be very careful.
Yeah, very good.
喂，
Yeah, just click on. So you can also
Oh, and this one is for
Zoom.
Zoom.
Yeah, this is for
Okay.
a local service called Share. It's around China.
Will be these talks available on Zoom?
Yeah. It is also broadcasted in YouTube. So
Oh,
most of them are.
YouTube. It's not fixed.
I can help you.
Yes, sure.
Start 7:40. Sorry, 7:40.
140 is the video time. but-
Okay, but we will start a
But,
minute late.
Okay.
because there are no-
Alexei is not here.
Yeah, I have
Yes,
checked
10
the slide.
minutes
It is working.
So now is the microphone.
For the local, this speaker.
So I have three,
Yeah, you can amplify this will amplify your voice.
and I need it. So where?
I can help you.
But where? Because
It should be close to your mouth as.
is the closest one should be this one, no?
Yeah. So
Okay.
you can, if it is not.
Now we
bothering you,
can.
then-
Can you hear me?
So I
No,
will
it's
turn
not.
it.
It's not.
It's in mute mode now.
Now, can you hear me? Okay. So now I switch
You
it
can
on.
put it in your pocket or something.
Okay. I have noticed. Con lo que no cuentas es que ellos se lo van a tomar con calma también, porque no les han, a Lesla no estaba su comida. Entonces él va a comer allí y no va a venir antes de. Tú tienes que esperar por lo menos 20 minutos para comer. Tú vas a comer aquí durante la charla. Sí.
Me da vergüenza,
No,
pero
pero lo
por,
tienes que
por lo
hacer.
menos la gamba me la voy a quedar.
Aprovecharé para decir burradas.
Pero muchas gracias por la organización.
La verdad es que es un pequeño desastre que la última sesión no haya nadie.
Y me ponen a hablar justo antes, sabiendo que yo luego soy la que...
Yo me alegro de estar en la última sesión, así no hay mucho lío. Además ya se ha introducido todo.
Pasaron también a todos.
¿A quién?
Pasaban
Sí.
a los colegas, no ha puesto, vamos.
No, pero él yo creo que quería ser. Una cosa.
Pasaban, quería ser el último.
Sí, Big Man es Alexander, pero le llaman Sasha, ¿no?
Sí, esa es como José. Que...
Ya, pero quiero decir, se lo llaman, no.
Ujú.
Es muy extrovertido, como ahora
Pero yo, como no tengo confianza con él.
Yo lo conozco, pero no sé, porque algunos, por ejemplo, Alexei, todo el mundo le dice Alexei.
Sí.
Normalmente se dice Alyosha.
Ujú.
Y a él le dice todo el mundo Alexei, ¿no?
Pero,
¿Por
por
qué?
ejemplo, Alexander Zhuk es Sasha. Pero Sasha es más coloquial. Si tú no tienes suficiente confianza con él.
No, pero aquí todo el mundo habla coloquialmente, sobre todo porque hay muchos rusos y los rusos muchos son muy activos. Este italiano con el que hemos comido, es que yo soy muy malo, no me acuerdo de su nombre.
Aunque estaba en izquierda.
Sí.
Flavio, el apellido, no me acuerdo.
Ya. Y,
Habló el lunes por la tarde.
y el que estaba justo a tu derecha, pero no inmediatamente, que ese es un estudiante.
El
Está
otro
allá.
no sé quién es porque lo acabo de ver.
Yo cené ayer con él.
El que estaba justo a la derecha.
Sí.
Ese ayer no. O yo no lo
No, el que estaba a tu lado es un estudiante.
Digo el siguiente.
Siguiente.
El siguiente ayer no estaba.
¿No estaba dónde? Sí. En la charla, sí.
El que estaba enfrente de él, sí.
Y
Roberto,
él,
sí.
él también. De hecho, él creo que ha estado todos los días. Ah, se me ha olvidado traer agua. Este es Sasha o lo después de ti, ¿no?
Sí.
Bueno, aunque haya 10, ya está. Bueno, 10 no, tienen que ser 12 apóstoles más Jesucristo, 13 tiene. Cuando entren 13 empezamos.
Federico no ha estado.
O está
Depende.
el que está de punto es Saposnikov. Este está siempre
Ujú.
puntual. Es muy amable ese hombre. Tú has dado 3 o 4 temas distintos
En la charla. He hablado de modelos clásicos, modelos
y luego
más
acabas
fenomenológicos.
con
Luego he hablado-
Wheeler de Witt al
Eso
final.
es.
Cuántico.
He hablado de varios modelos fenomenológicos.
Yo quería hablar con Mujanov, lo que ha preguntado, porque él tiene una idea clara. Lo que hizo una pregunta retórica para poder hablar. Pero
Lo del H0, pero ahí es cuando estaba el especialista, él estaba ahí y
Ya,
no
ya.
le dijo nada.
ya. Sí que habló, ¿eh? Ayer hizo preguntas, pero
No, pero en la charla de Manus no.
creo que tengo una falta de ortografía grave.
No
Ah,
lo
está
veo.
bien,
No,
está
no,
bien.
está bien, está bien.
Ya estamos 13, ¿eh? Este, 18, 19 y 20. Ya casi somos mayoría. Entonces, si empezamos ahí 50 y algo, acabaré a y 20. No, hay
te
media, hay
enseñaré
media,
antes.
hay media. Yo acabo y media. ¿eh?
Pone
Mínimo,
5,
mínimo.
10, 1, lo que esto te ve, lo que tienen tanto. Ah, vale. 10, 5 minutos.
Y 1.
Ay,
Sí, en la comida. No, se me ha soltado, no se ha roto. No sé si te fijaste que lo estaba buscando en el suelo. Al ponerme de pie, espero que no se note.
We'll start in a minute. We would start in a minute because there was almost nobody. Almost nobody. Because there was no time for lunch.
Was the classical vacuum.
Yes. And I didn't have lunch. Because there was a problem with my dog. A problem with my dog. Like, that's a bit. No. Not reuse them.
So you,
You cannot reuse them.
No, we can reuse only until 10 of July. Yeah, but it's an if you return everything, it's too much.
Okay, if it's okay with you, we can start. Welcome everybody to this afternoon and last session. And our first speaker is Manuel Arcelay, and he will tell us all about that he got super remarkable fields.
thank you very much. I would like to start thanking the organizers, especially Alexei, because it's a tough work organized conference like this one, and he did it very efficiently. And I also thank for the invitation. I'm going to present a work which is done in common collaboration with a few people who are here, like Lesla, and others which were supposed to be here, like Ilya Shapiro, and some others, Gustav Crane, Fernando Garceto, and Fernando Esquerro, which is a PhD student. So the goal will be to answer one question raised by Stephen Hawking many years ago. Alexander Bigman mentioned another work, later one, by Hawking, and the paper is quite modern. He addresses all the problems we are discussing here. But the question is, who is afraid of ghosts? Higher derivative, of course. And I should say that I was afraid, but I'm not, because I'm here. Otherwise, the talk is gone. So I'm not. But I must say that I'm still a little bit afraid, because I never applied for a grant with the word ghost in the title or just in the summary. And I think I know quite a lot of people working on this subject, and they also have the same fear. So you can put actions, you can put WIMPs, whatever, which is almost with zero probability of existence, but this gets granted. So what I'm afraid that putting ghost, except if you are Steve Hawking, it will not get funding. Okay, so still a little bit afraid, but not much. And I also know that many of you are not afraid because you have seen the list of talks, and I don't think it's an irregular amount of talks without using this word. So the answer is quite easy, but to answer properly, you need to have a classification of ghosts, because there are many kinds of ghosts. So I will discuss few of them: bad ghosts, good ghosts, and super good ghosts, shy ghost, and finally, ghost in love. Okay? So, and there are many more, which are, even during the talks, there are other ghosts which are not included in this category. So, and the second field is high derivative. So ghosts are constrained to be discussed in this approach, high derivative, and I will restrict to local high derivative theories. So essentially polynomial modifications of standard local field theories. I mean, I will not spend much time trying to motivate you on the subject because you are already motivated, but I would like to emphasize the fact that standard field theories, not talking about gravity. So our motivation is to understand quantum gravity, and this is a framework, higher derivative is a framework which need to be explored to as an avenue to understand things in quantum gravity. But in a standard field theory, it's also interesting subject because there are many effective field theories which involve high derivatives. For instance, in low energy QCD, and also maybe the standard model is not complete. So it's not excluded that the completion of a standard model will require higher derivatives. I will talk about that. So a standard model is composed of massless particles, zero spin particles, the Higgs field, but is the only one which has this property, and until very recently we were not aware that this was a physical particle or field. You have the classical spin particles, which are well known, and these are known for a long time. Electron was one of the first, and then we have a spin one, which includes all gauge fields, all interactions. But it's easy to complete all of these theories by including higher derivative terms. And for scalar fields is the simplest case, can be down, but it can also be down for spinorial fields and for gauge fields. So I will focus on in spin 0 and spin 1, integer spin. So, but we know that if you complete these theories with higher derivatives, the theories start to be populated by ghosts. And these ghosts, as you know, are unfriendly, most of them. They are bad ghosts. And some problems you have been discussing these days concerning causality and unitarity, which have been addressed by many people here in the audience. So let me just start with bad guys. So bad ghosts. So the typical example is just the one which has been discussed here, which is higher derivative modifications of standard scalar fields. And these modifications are, here is written in Euclidean formalism. So this, instead of box, the Lambertian, I have this Hodge operator, which has a minus sign compared with the box, okay? But this is a typical example, the simplest case where you can discuss the pathologies associated to ghosts. And these have been one of the first higher derivative fields theory which appeared in the early 70s. At that moment, this was used as a regularization of scalar field theories. But now it can be looked from the perspective of real theories, which are completed in the UV by higher derivative terms. So these theories are UV finite, provided that you have enough number of terms in your polynomial high derivatives. And the reason for being UV finite is that the propagator has a very nice behavior as well. But you know, the problems have been, you know, so I will not insist. There are many problems, and usually they are associated to ghosts, and we call it this ghost, bad ghosts. But there are solutions for this problem, which have been here discussed, for instance, for Poland and others. But let's keep it this category as bad ghosts, because there are nicer ghosts. And one of the nicer ghosts we have is this one. Well, sorry, I missed this slide, which is essentially, I will classify bad and good ghosts according not to my taste, but according to some physical properties of the system, which are associated to fundamental properties like positivity in the Euclidean formalism of the rather positivity, or Chern-Lehmann representation of the two-point function and higher order functions of the theory. This is an analytic way of classifying the pathologies of the theory, and is very efficient. So let me start with what does it mean. So both properties, Osterwalder-Rader reflection positivity and Chern-Lehmann decomposition, can be related by this theorem, which tells you that they are more or less equivalent if you add some extra analytic properties to the game. And essentially, what it says for the two-point function is that if this two-point function has to satisfy reflection positivity, has to be of this type as an integral of a normal propagator, which a mass which is variable and with a density for each value of the mass, which is positive. You know that. So, but the nice property was discovered by Bieder in his book in the early 30s of the past century, which says the following: this guy as a two-point function admits such a representation, provided that all these series of inequalities are satisfied. The simplest one is this one, is the one I will use more. But there are complete series you need to satisfy. The proof of this theorem is very simple. In fact, it can be done in few slides in one way. Just the opposite way is harder, is what he did. So the first one is very simple. You take this second derivative, the first derivative of this product, and you just after some algebraic manipulation, you end up with this expression, which is obviously positive. If you consider the higher derivative of so the signs are alternating, even derivatives are negative, the other ones are positive, but this is taken into account in this sign factor here. And then immediately, if you do that with this combinatorial factor, you end up with a similar integral, but with larger power in the denominator, which is always a positive number. So you can prove that if this number here, Cn, is positive, everything is okay. And this number is computed here for the first part of the series, and you see that they are always positive. But you can prove that all of them are positive. So but this is a very efficient way of classifying pathological theories or not. And the pathological theories are associated to bad ghosts, okay? In principle. So this allows to classify these theories. But as I said, there are also very super good ghosts. This one is very old. I think is the first ghost which appear in the literature, and is holy ghost, so no complaints about that. But we have some other ghosts which also appear earlier, which are good ghosts. These are the Faddeev-Popov ghosts. We know that these are very helpful and they are harmless. So the nice property of Faddeev-Popov ghosts is that they decouple from the physical degrees of freedom. If you are using this BRST symmetry, you can prove it, but you can do something more explicit. Make a field redefinition, and then in this field redefinition, the theory is split in one sector, which are the physical degrees of freedom of the gauge fields, 2 degrees of freedom for each component, and the ghost sector. And the ghost sector, in that case, is a free theory, a Gaussian theory, ghost anti-ghost, and the BRST symmetry is just a rotation between these two sectors. So in that case, you immediately understand that if you preserve that symmetry, physical degrees of freedom are completely decoupled from the Faddeev-Popov. If you now make the field redefinition, you have determinants, you recover the Faddeev-Popov determinant, and you recover the ugly expressions for the theory in the standard local formulation. So in that sense, we agree that these are Faddeev-Popov ghost, and it has been shown in the literature that the 2-point functions is okay, has a Cherel-Lemma representation for even non-abelian gauge series. So let's now go to the next category of ghosts, which are the psi ghosts. These are not so well known, so let me just spend a few minutes introducing them. So let's analyze the completion of gauge series. This is what I refer to the standard model, sector spin 1. So just add to the standard Young-Mills theory. I mean, you can add quarks and so on, but the main points you understand in this simple scale. So you have a higher derivative term in a very special form. This, let's say, box N Euclidean is just this Hodge covariant operator. It's one choice. But I will use this choice. You will see why. And then you need a scale just to take into account that the dimension of these new terms are different from the one you have here, which is conformal invariant. So this explicitly, this operator looks like that. Has a piece which is the ordinary covariant differential square for scalars, plus some commutator with magnetic, chromomagnetic field. But the coefficient in this expression is physics, is 2. Okay. The advantage of this formulation is that if you have here instanton solutions, these are also solutions of the equation of motions with this completion. So you keep a lot of the theory of standard Young-Mills. And of course, this kind of theories were also introduced by Faddeev and Slavnov, but not as a completion of any theory, just as regulators of a standard Young-Mills theory. So what happens in these theories? You can compute everything in perturbation theory, in particular the 2-point function. And it turns out that you have, even if the theory has higher derivatives, you cannot skip the fact that one loop divergences are there. So this has been discovered by Saint-Just and Benny Lee in the early days of gauge series. One loop diagrams are still divergent no matter how many derivatives you put in the Lagrange. So the expression for one loop calculation is of this type, is divergent, as you say here for the dimensional regularization 1 over epsilon, but it has a coefficient which depends on the number of higher derivatives you put. So for n larger than 2, which means 4 extra derivatives, it takes this expression, which is independent of alpha gauge. This is computed in alpha gauge. And then there are 2 special cases, which is n equal 1, where you cannot apply this general formula. You have to do it in this specific case, and you get this number. And also in the pure Young-Mills, you get a strange thing, which only occurs in that case, that the coefficient here depends on alpha. Okay. By the way, this has been done in collaboration with Leslie, which is here. So then you have to renormalize the theory, just removing the poles, and then you have this pole, and you add a finite part, naive part, which is just it's another scheme of renormalization, which has the ratio between the lambda QCD and the lambda, which is the parameter where the higher derivative terms enter to operate. So once you have this, you can, this is the control term, is proportional to the Young-Mills part, is the only divergence of the theory. You remove just by removing that, and adding this finite part, and then you compute the beta function of the renormalized coupling constant, and it turns out is given by this expression, which is generically the Cn was given in the previous slide for n larger than 2, and for n equal 1, you have a special value, we were there, but for n equals 0, you don't have the same, because there is a field renormalization in that particular case. Only in that case which fortunately liberates us from the alpha dependence. So finally, the coefficient of the beta function is also gauge independent. It's very nice, it's well known, but it's remarkable that higher derivative theories don't have this problem because there is no field renormalization, no need of it. So the second remark is that all these coefficients till 4 are negative. From that on, they are positive. So asymptotic freedom is gone for large number of derivatives. It's only kept for a finite number of higher derivative theories, which is quite remarkable. So if you look now for the physical observers, the 2-point function, which is finite, you have a form factor, which is computed here, which is of this form, which has one part which is depends on the high derivative scale, lambda, which is, I will take it 1,000 times larger than 1,000 TeV, but not to compromise the current phenomenological data. And then you have a finite part which involves the QCD constant, which was introduced in the normalization scheme. So the interesting thing is that this coefficient Bn are not exactly the Cn before. They are, to some extent, we subtracted the C naught. And then these are the values for n larger than 2, and these are, of course, for the case of pure Young-Mills, this is 0, this term is not there, and this is just the standard beta function of QCD. Whereas in the one-dimensional case, this coefficient now becomes alpha dependent, because if you also here in Bn, because you subtracted the standard Young-Mills part. Okay. Then there are two regimes to analyze this form factor. One regime is the one which is for very large momenta, larger than the scale of the higher derivative terms, considering this as an effective field theory, but here is a fundamental field theory. So the beta function in that case is given by this expression with the coefficient Cn, the one which appears, not the Bn, but the Cn, which appears in the analysis of the divergences. And then there is an interesting intermediate region, which is between this lambda and the lambda QCD, which might be very large, 6 orders of magnitude you can have. So in this regime, the beta function is this one for all the theories. It's just the QCD one. So this is the one. And then you have the infrared part, which you have to analyze non-perturbatively for momentum lower than the lambda QCD. So this is the picture. You have a beta function in the 2-point factor, logarithmic dependence on momenta, which has the same slope. It's the same beta function till the energy of lambda, which, as I said, I take it 10 times, so million times larger than giga electron volt. Okay, then from that point, the theories start to deviate according to the number of derivatives you have. All these theories do have negative slopes, asymptotic freedom. You see n equal 4 is the last one. From that on, you have positive slopes. But the remarkable thing is that the n equals 0 is quite close, and the more asymptotic free theory is n equal 2. Okay, let me spend a few minutes because I'm getting slow. With a small generalization of that, if instead of having this Hodge operator, which is canonical, let's say, you have a modification of that by including extra commutators with field F, you can parameterize that by the parameter lambda. Lambda equal 1 is the previous case. And then you can compute the same thing, all the coefficients of the divergence, renormalize again on the same lines, and you get this picture. So the blue domain, this plot is, there are two parameters. One is the number of half of the number of extra derivatives. Derivatives are 2n. And lambda, this extra parameter which appears in the covariant differentials. So you see that the previous case was this red line. We have very few theories which were asymptotically free, which are this n equal 2, n equal 3, n equal 4, n equal 1, 2, and n equal 0, okay, which are not plotted here because lambda is 0. But then you see that the dependence on lambda closes this window. So for theories with a large number of derivatives, there is a value of lambda which where if it is larger than this value, the theory is not asymptotically free. And there is only one special case, which is n equal 2. This theory is very special because it survives for any value of lambda. It's the only one. And you remember was the most asymptotically free theory because it has the largest negative beta function. So this is quite remarkable, but you have many theories which are asymptotically free, much more than before. And in particular, in the borders of this domain of asymptotically freedom, of course, the beta function jumps from being negative to being positive. So in the border, these blue points, you get 0. So these are points where the beta function is 0. So they are conformal invariant points and where the theory is finite. So in that case, you don't need to renormalize the theory because it's finite. Okay, it's a side remark. And these points correspond to what is written in this table. Okay, but the Bath knew about having this lambda parameter. If this lambda is not equal to 1, instantons are no solution of the classical equation of motions of this family of completions of gauge series. Okay, now the point of Gauss. So we have the epoch of Gauss in this theory, we rest the symmetry, these are good Gauss, but there are extra Gauss because we have a larger number of derivatives. And this larger number of derivatives play a fundamental role in the behavior of Gauss in these theories. First remark is that there is no field, so the higher derivative terms do not have divergent contributions, only the Young-Mills part. So it means that they need not to be renormalized, okay? But in these terms appears the product of lambda, the parameter, and the coupling of the QCD. So if the coupling is renormalized, the parameter lambda has to be normalized the opposite way. So it goes to infinity in the infrared. And remember, this is connected with the mass of the Gauss. So if the mass of the Gauss goes to infinity, you are liberated from Gauss, in principle. But you have to compute. Okay, let me just go faster. And you compute that in the 2-point function, which looks like this, which is much more positive than the previous one. I mean, the 3 level. But what happens is that it seems that in the case of asymptotically free theory, there should be a problem with the limit of the Gauss having infinite mass. Let's see. We go to the safest place, which is computed Schelling-Lehmann positivity according to wider classification. No, I mean just the 3 levels. So you have the 3 levels. Yes, you have a lot. No. It's not written here because this is a one loop calculation. I mean 3 level. At 3 level, you know that you propagator expands and you have Gauss. Okay, like in the scalar case. This is what I mean. So here, what you have is that this is the good news. So you have for all asymptotically free theories, this parameter is, so this first derivative of Wither is positive, which is good for having a Schelling-Lehmann decomposition, okay? The first case where the theory is not asymptotically free is n equal 5, and you see it gets negative at some scale. What is the scale? Exactly the lambda scale, the lambda of the mass of the Gauss. So the non-asymptotically free theory are pathological already at the scale of lambda. But the The other theories, which are asymptotically free, they seem not to be affected by this problem, but that's not complete true. If you go beyond that scale, you have n equal 4 is the first one developing a peak. So in the negative, so they do not match the Witten condition. And the last one is n equal 2, this magic theory, which survives 3 orders of magnitude. So it means that the ghost problem do not appear till 3 orders of magnitude beyond the scale of the 3-level mass of the ghost. So this is what I mean. The mass of the ghost is running to infinity, but not too fast. So there are still traces of pathological behavior at larger scale. This is what I call it shy ghosts, because they do not appear at first sight, but they are behind the door, okay? Very far. So these are the second family of ghosts. So, and now let's come to the last category, which is a very nice one and maybe more interesting for you because it has to do with gravity theories, is the ghost in love. Let's consider now a gravitational theory with 6 derivatives. And well, you have here, I forgot to put the parameters in this term here, but you can understand that there are parameters which you might choose. And you know that, the theory is not like Young-Mills. At one loop, the higher derivative terms get divergences, but they can be normalized, and the lower terms in dimensions of derivatives, well, require to include 2-loop or 3-loop corrections for removing the divergence. So you fix the gauge, you use the RST, whatever, but you remember you have in this theory the physical degrees of freedom still are the graviton degrees of freedom and the scalar here, okay? And so, but the interesting thing is that if you focus on these fields, on these sectors, which are the physical ones, the theory is quite similar to this scalar theory here with 6 derivatives. So let me just focus in this toy model. Of course, in gravity, you have much more terms here, but let's stop at 4 order. So then you can formulate this 6 derivative theory in terms of some decomposition the field into, let's say, auxiliary fields, phi 1, 2, and 3, and each one has associated, let's say, a dynamics as an ordinary particle or a ghost, and here you have 2 ghosts, and you have one real particle, which is the graviton, and the couplings. So these 2 particles are ghosts in a special choice. They do have complex conjugated poles. So let's restrict to the case where this happens. This also can happen in 6 derivatives gravity, not in quadratic gravity. In quadratic gravity, it cannot happen, okay? So you can compute now, this has been done by many people. I don't quote here all of them. Many of them are in this room, but these are the ones which, let's say, started the game. And you have this composite field of 2 auxiliary fields. This is local. It's a very nice property. And you compute the 2-point function of this composite field. And this you can be done because it's trivial exercise. And you get that at one loop, this is the result. Of course, it's logarithmic divergent. You have to renormalize. Here is the minimum MS bar subtraction mechanism. But there is, the price to pay is that there is a free parameter mu. You have to fix in different according to this scheme. Well, the result is that if you sum over this change of loops, you get this form factor for the 2-point function, which is can be computed explicitly. And there is a coupling. So for that, here in this vertex, you need the 4th-order coupling, which was in the Lagrangian. here. This one. Okay, this one couples the two auxiliary fields. And if you take this into account, you can complete the chain of loops, sum up a geometrical series, and you find this formula. Well, this is the paper where this is done. So now you try to pass the Wither test. Are there ghosts? Because the first remark is that this correlator tells you that there is in the denominator here, you can have a 0. So it means that a 0 when P is pure imaginary. So it means that you are looking at the pure imaginary poles of this expression. This you find, and depending on the scale mu you use, and the coupling, which this G I didn't introduce, but it's just this lambda 1 over factorized by some numerical factor 4 pi square. And so if this is not very large, this plot is for a specific value of this coupling, for order coupling. You get a 0 here, which is a mass of order 0.88. So close to 1, but 4 below. And in this case, you assume that the poles are of this type. Yes, normalized. It's just to put numbers, okay? So you have this pole, which means that in this correlator, you discover that there is a massive particle, real particle, because the residual of this 0, fifth pole, is positive. So it's a real particle. And not only that, so this is the... No, this is not. This is a two-point function. It's not the coupling. It's not the renormalization of the coupler. Yes. I'm not renormalizing the coupling.
I mean, the correction should be by this perturbative computation should be as smaller than the one.
Yes.
While you are taking seriously the pole when everything is the same order.
Well, you can change also here and to put lower coupling in the theory. Yeah, I agree. So, but this plot, I took it from one of the several plots which are, there is another plot where G is lower than 1, okay? And you still have, so the essential message is that there is a critical value for the coupling. If your coupling is larger than that, you have this cut here. So you have this 0. And then, but you might be still worried about what you said. Still not going beyond one loop, just keeping one loop. Okay, this is what I call lowest, because this means that there is a bound state of two ghosts in this theory for these specific values of the parameters. And then this bound state behaves as a particle with a small mass, which is 0.88 in that particular case. But the question is that safe? So this is the behavior of the form factor according to the momentum in Euclidean space. Now I don't have this going to the complex plane. So yes, it looks nice, but what is nicer is that it has this Chern-Lehmann decomposition. So it's a real particle. And it's composed of two ghosts, so the two ghosts condensate to a particle which has, and this particle does not exist if you have real masses, only if you have complex conjugated poles in the original 3-level Lagrangian. So the same happens for the complete form factor summing over all loops, and we expect to have the same effect in quantum gravity. With that, I conclude that not all ghosts are coming back to the question by Stephen Hawking. You should not be afraid of all ghosts. They are many families. Some of them are friendly, other ones are super good. And some of them, like these ones, provide a condensation which generates let's say, keep the ghosts bounded, and it's not complete, that they do not affect the rest of the theory, but still this has been conjectured for a long time, but there is an explicit calculation which shows that this has a channel lemma representation. So in Young-Mills theory, we have seen that they provide a safe domain of energies till very large energies if they are asymptotically free. And in this gravitational case, well, this was not gravitational, but this mimics what happens in 6 derivative gravity. It tells you that perhaps since they have a mass, they of Planck order, by the way, I didn't put units, but it's Planck order mass. So you might suggest that probably this is a candidate for dark matter, and the answer is not. It's impossible because, I mean, you should guess, but let me just remind you what is the argument. If you evolve before inflation the density induced by this condensate, you let evolve at present as after inflation, you get the fraction of the vacuum density of the density of matter induced by this ghost is a tiny fraction of the matter of the universe. So it's not a good candidate for dark matter, but nevertheless, it keeps the ghosts in a safest place that they were at the beginning at 3 level. So the total message is that what you have at 3 level might be modified by interaction. In Young-Mills case, it's clear that the ghosts are not completely erased, but they are postponed to very high energies. And you can even work to have till granularified scales, which will be nice because there you don't know what is happening. And in gravity, you have, let's say, ghost a little bit apart from the rest of the degrees of freedom. And that's it. Thank you very much. No, this is in the Young-Mills case. Here, not. Here, no. It's fixed by the renormalization scheme you choose. And also the coupling, which in gravity is given by other properties.
Yeah.
Because in gravity, you choose the quartic coupling. Yeah, but this bound states,
Yeah, but
they satisfy the wider inequality. So in principle, you have to find other correlators which violate that inequalities.
well, I think the vacuum can begin the bound state of ghosts. And the energy is positive.
No, the vacuum is zero ghost. So vacuum is without ghost.
Can keep the sure bound states. Bound state we talk about is the positive energy state.
Yes, but not to the vacuum. I mean, you pump up one condensate, so a bound state of 2 go. And the nice thing is that how do you see that the real poles do not contribute? It's very simple argument. You have in this Chern-Lemon decomposition, you have a branch point. This branch point for real poles in 6 derivative terms start in 4m. So it means they are free. So the ghosts are free. Whereas here, they are in lower energies, which means that there is an interaction and they are bounded. The energy is lower than the sum of the energies of the different ghosts, even if they are negative. Oops.
Hello, everyone. Thanks, Mariam. Since I have 3 mics, I'm going to speak about 3 topics. So this is based on mainly there is observational part, which has combined with some theoretical part. It is based on the work done with Enrique Gastañaga, and then the theory parts are in collaboration with Gio Marto. Basically, what I will speak about is QFT encoded spacetime and how it affects really our world. I will show some new revelations that CMB has been telling us from last 3 decades. Okay, so my plan is the following. I will first go through completely observations. I want to entertain you with a lot of pictures. Then before I go to the theory part. So, okay, well, take away message number 1 before I go to everything. Question assumptions, always pay attention to small details, because what I'm going to speak about is something involves gravity and quantum mechanics, and we have to be very careful in understanding this subject. As you all know, you are all experts of quantum gravity, and well, you have to pay attention to small details in the sense I give you this Alice in Wonderland. So when we want to understand gravity and quantum mechanics, we have to pay attention to the small issues which are very important in the context of quantum mechanics. For example, the concept of time. Okay, fundamental questions. Out of all fundamental forces of nature, gravity is the weakest force, which you all know. If you look at standard model of particle physics, there are 3 concepts which play a huge role: parity, time reversal, and charge conjugation. And especially parity violation in the weak interactions has played a huge role for building the standard model. And this particular experiment, Wu experiment, done by this excellent scientist from China, she has opened up completely a new understanding of quantum theory, quantum field theory, which has led to building standard model, as I said. So the experiment proves that in the beta decay, parity is violated. Well, these are details of experiment which are not much important now for the moment. So, well, when this outcome of this experiment is heard, very big scientists, like for example, Pauli, rejected, no, there cannot be any parity violation. But actually, it turned out to be true. There was parity violation. And after the success of standard model, Abdul Salam described the experiment on par with Michelson-Morley experiment, which has led to the special theory of relativity. So this experiment is that important. Now the question, because gravity is the weakest force, what is the status of discrete symmetries? What about parity? If we have quantum gravity, do we violate parity? That's a question we will try to understand. Okay, this is just motivation. I jumped to observations now. Next few slides, completely pictures of CMB in different ways. What is CMB? Well, it's basically temperature fluctuations. This is a map of CMB. You might think it's look different because it is smoothened to observe the large scales. Okay, this describes temperature fluctuations, which we normally decompose into the spherical harmonics. These ALMs measure the angular power spectra. So basically, you measure angular correlations all over the sky. And this is what we measure. Okay. So, by the way, all the things which I will tell about observations is you can find the details in this paper. So, how do we get this? What is the physics behind? Well, this is exactly action of gravity and quantum mechanics. By the way, it's not Planck scale physics. When I say gravity and quantum mechanics, it's QFT in curved spacetime. Quantum fluctuations evolving during inflation. Okay. So, some role of quantum mechanics has created this. This is something undebatable. as Slava has mentioned during his talk. It's true. So now let's look at this map very closely. First of all, when you have a temperature fluctuation, so temperature, you can write it as symmetric and antisymmetric part. When you have any function, you can decompose into symmetric and antisymmetric part. So symmetric part is t and t minus n, and the antisymmetric looks like this. So it satisfies the following properties, just a simple decomposition. Now, what we do, so the full map of the sky is basically combination of symmetric and antisymmetric, which is easy to check. Now what we do, we'll separately look at the maps of antisymmetric and symmetric parts. By the way, what I'm going to describe is some visualization of the maps, but then later I will go to the details of quantifying some hidden features, okay? This is the full map, and this is the antisymmetric part of the map, and this is a, this is a symmetric, this is antisymmetric, this is the full map. Pay attention to these two. If you look at antisymmetric, because it is antisymmetric, it's visually nice to see, for example, if you have this C1 structure, large scale fluctuation, which is cold, and a similar inverted shape you can find here, H1. You can go to C2, for example, C2 is here, and H2 is here. So you see images, cold and hot spot, which are like inverted mirror images. So there is a cold spot, and there is a mirror image version of it, but it is a hot spot. This is not surprising. This is antisymmetric map. That's the way it has to look. But what is surprising, if you look at this map, the full map, there is a very close resemblance between the full map and the antisymmetric part. So when you combine these two maps, you are not supposed to get the original full map should not look like neither this nor this. But what we see in the CMB is that this full map it looks very much dominated by antisymmetric part. For example, you see this structure here and this one. By the way, this region is just the antipode of this region. Basically, it's it's like a CMB sphere. You go, this is at, for example, at angle theta phi, and this is angle pi minus theta and pi plus phi. These are antipodal points in the sphere. So the fact that CMB looks much more odd than even is surprising. Why so? That's a question we will hunt for. And how much it will look more like this? It's 20% effect. So CMB map looks 20% more aligned to the odd part of it rather than even. So what physics can explain this 20% is a question we hunt for. Okay, we can look at this map again in a different way. So this is the full map, but now you go to a particular north and south. But this is just for a visualization. The CMB looks parity asymmetric. That means the odd component is dominant in any direction. So this is just another way of looking at it. So you have north and south. This is the full map, and this is the antisymmetric part. You see, they look very much similar. What does this suggest is that the temperature field has a pure antisymmetric component. You see the delta T, which has a property like this. Remember, the antisymmetric component has a property. So this one, okay? So there is an additional component for the temperature field, which is purely antisymmetric. That means there is an excess of odd component. That's what the data suggests. Okay, we can go to the much more quantifiable way of defining this. Why odd? How much more odd excess in the map? Okay, this is just, you can see, for example, let me compare whole data from Kobe to Planck 30 years. Kobe satellite has when it has first seen the CMB, and Kobe has a sensitivity to look for correlations greater than 9 degrees. So this is the Kobe map, and this is W map, and this is Planck. you can clearly see in the previous picture I have shown this region cold, hot, antipodal points. And you can exactly see the same feature in the Planck as well, and also in the W map. And all these additional points are the small scale temperature correlations. So what does this mean in the angular correlations, basically the CLs, angular power spectra? This corresponds to large scales, that means greater than 9 degrees, you see? And if you look at this region, there is oscillation between even, odd, even, odd, even, odd. That's what data is pointing out. You might have seen a lot of quantum gravity approaches tried to explain, there is a power suppression at low multipoles, some new physics. No, there is no suppression. It is actually, the picture is totally different. There is an oscillation, even, odd, even, odd, even, odd, which is related to parity, right? Yeah. I will explain that. I will come back to that, sir. I will go to that. I know the question. I anticipated it, and that's the next slide. I will explain. Everything you ask, I anticipated all the questions. So please hold on, few more slides. Okay. What is CMB? Well, CMB, we measure this. Well, actually, we measure correlations in the position space, do the Fourier transform, and compute CLs, to be strictly speaking. Okay, at the end of the day, this is what is important. And this is power spectrum. Some initial conditions come from inflationary quantum fluctuations. But let's put the inflation aside. People already know what this power spectrum should look like, even from before inflation idea was formulated. It has to be scale invariant, well, nearly scale invariant. This is the form which was postulated. Indeed, this can explain a lot of the CMB data only for correlations less than 1 degree. Okay, so when we say success of inflation, explaining this, getting this power spectrum, yes, it's only less than 1 degree. But if you go to larger than 7 degrees, 9 degrees, there is a large scale dependent features which are not considered seriously because they are thrown away under the carpet of cosmic variance. I will explain why we throw away, because there is no theory that predict exactly large scale features. Okay, but okay, well, you can say there are several models. When we say theory, the theory with the same number of parameters as the scale invariant power spectrum and lambda CDM. Okay, so when people say cosmic variance, it is calculated from this model plus lambda CDM. And okay, data is within this cosmic variance, it's fine. You don't seriously think about it, forget. Okay, well, this is like something very surprising feature in the CMB. We are throwing away by hand. Well, this is like maybe premature, throwing away out with bathwater. I argue that there is some physics which is hidden behind these features observed in the CMB. So to answer this question, it will come. I'm not denying this is NS is totally fine. Less than 1 degree is a small scale, it is averaged, and NS is perfectly measured. There is no doubt about that. I'm not saying about this. I'm talking about the low multipoles. Low multipoles less than 30 or even 20. Okay, so I'm not denying everything. So it's an amazing feature. We measured it, and of course, this must be correct. There is nothing wrong with it. Okay, but my issue is about low multipoles, and there is parity asymmetry there, which I will explain. And I will again come back to this issue of cosmic variance. Please hold on. Okay. The point is, suppose if you have a theory which has exactly the same number of parameters, but it reduces the cosmic variance, then the theory is better than, most likely explain the low multipoles than the standard scale invariant power spectrum, right? So that's one way to beat the cosmic variance. You need to be very careful. You need to be very careful in formulating the theory that just goes and hit the data. So this theory, which is called direct sum inflation, I will go to the theoretical details. Please bear with me. I want to present the first how it performs with the data. Okay. So let's take this standard inflation or scale invariance power spectrum, lambda CDM, and this is observable called Z. Basically, it is temperature at N, temperature at minus N. Okay, just a correlation of that. So this is all the data maps, the several maps of the Planck, and these are the theoretical simulations from standard inflation and lambda CDM. First of all, you have to understand what do we mean by simulations. Okay, we have only finite part of the sky, and we are measuring angular correlations. When we do simulations, we average out all over the sky, and especially the phases. Okay, and there are several ways to put phases here and there, so that's how we do the simulations, and this is basically 1 sigma region. You see the data kind of going out of this theoretical prediction, and then there is a new theory which goes very much in line with the data. Okay, I will explain the physics behind it. Please bear with me. So there's a long way to go. Let me finish the observational part. So it looks, the theory presents better than the standard inflation, but of course, this theory does contain the scale invariant power spectrum that is exactly less than 1 degree, and it predicts exactly the same NS. Okay, that is around multipole to L equal to 200 roughly, or less than 1 degree. Okay, this is a plot which is known from 20 years from WMAP data. So basically, this is correlations between angular correlations. Okay, so temperature at N1. So you look at this direction, look at this direction. So there is an angle N1 minus N2. So this is the plot of the angular correlations, and this is all the data. All these color lines. Okay, these are the different maps of the Planck. And if you look at the standard inflation plus lambda CDM parameters, you see this black dotted line. It goes here, but all the data at 180 degrees shows something. It has to go this way. All the data consistently goes this way. And even if you take cosmic variance issues, but it kind of goes away from almost more than 2 sigma. But I will go to the sigma calculations in more detail. Just bear with me. You see this feature. Why the data is showing this? That's the question. That means basically, because it is at 180 degrees, it is something again related to parity. Okay, I keep repeating the word parity because theory is completely about understanding quantum fluctuations in expanding universe. And we design quantum fluctuations by careful understanding of parity and time reversal transformations. I'm giving a clue of where we go from the theoretical point of view, but you see this red dashed line goes very much like the data. This is basically the direct sum inflation. So this is second evidence of why this one performs better. Okay, well, you want to see equations, right? You're tired of plots. Let me show equation what matches the data. So even CLs have less power spectra, power spectra is a bit less. Odd CLs, it is enhanced due to some physics, which I will explain again. Okay, and the enhancement and suppression for odd and even is exactly given by this, and this NS is exactly corresponding to the K star 0.05 megaparsec inverse. So this is related to what we exactly precisely measure. That is indeed inflation consistent with inflationary prediction. Okay, and this expression is derived from a new understanding of quantum fields in curved spacetime. I will go through the derivation a bit more later, but the important point is this has no new parameters. It just depends on NS. Okay, you can try to understand why inflation is quasi-de Sitter. So 1 minus NS actually measures like a departure from quasi-de Sitter. So somehow quantum fluctuations evolving in the quasi-de Sitter carries some features in the large scale leading to parity asymmetry, and that's what is hidden in this formula. Ks is basically the scale distance to the last scattering. So you have this is the, when you have a distance to the last scattering, this is exactly the 7 times 10 power minus 5 megaparsec inverse. So you convert. Yeah. Yes, so it is of the order. So, but it is basically related to the distance to the last scattering. Okay, let's again go through. You want to see mathematical expression, right? Another one. Power spectrum in the direct sum inflation is basically this one, but it has more power spectra at one point, and its parity conjugate point less power spectra. So there is an asymmetry at parity conjugate points in the CMB sky. This is what the expression derived. And if you look at this carefully, so this blue line is the power spectra that gives you the odd multipoles, that is XS, and green is the even multipoles. If you take the average, you get exactly the scale invariant one. So if you combine these two, blue and green, this is the standard inflationary power spectra. Okay, I know maybe you want to know why it is like this. Okay, I will go to that. So this direct sum inflation exactly gives this oscillatory power spectra, which is the angular power spectra, which is exactly seen in the CMB data. Okay, this is the final slide of observations. Okay, now, as I explained, if you have a theory that gives less cosmic variance and that goes more in align with the data, then surely the theory performs better. That means the issue of cosmic variance is not related to observations, actually is related to theory, because cosmic variance is computed from theoretical CLs and then plotted. That's what my observation people do. But because here we have two theories, direct sum inflation and the standard inflation, okay, we have two theories, equal number of parameters. Now we have a fair way to compare with the data. What we do, we take what is observed values of CLs at low multiples and do data simulations. And then we do theory simulations, that is direct sum inflation. And also we do simulations of standard inflation. Basically, we do simulations like 10 power of 6 simulations. And what you see in this plot, so these are all the observables that characterize parity asymmetry in the CMB data. Let me explain what it is. RTT is the ratio of power in the odd multipoles to the even multipoles. Sorry, it's opposite. Even to the odd. This is one parameter that characterizes parity asymmetry in the CMB in the harmonic space. There is this one, Z, is characterized parity asymmetry in the position space. Okay, and there is another one called skewness. Now, there is another quantity which is quadrupole, the first multipole, which is the first point in the CMB. And what is remarkable is that CMB has been telling us from last more than 20 years, quadrupole is much more lower. Look at this point, the first point, it is much lower than what this green line predicts. So everything matches here, but there is a huge uncertainty here. So the theoretical prediction going very far away from the data points. So CMB preferring low power in the quadrupole. If you have a theory that predicts low power in the quadrupole, surely it is most likely better than the standard inflationary power spectra. Sorry, I'm repeating a lot of statements, but it's important. Now, let us look at this RTT theory data simulations, blue line, direct sum inflation, green, you see the perfect overlap, and the standard inflation, which goes quite off from the data. The same happens for the Z1, Z3 skewness, and when you go to quadrupole, you see it's not perfect overlap between direct sum inflation and the data, but surely it is much better than the standard inflation prediction. So this direct sum inflation predicts low quadrupole compared to standard inflation, because this theory really is sensitive to discrete symmetry violations during inflation. Now, the same thing we have here is in terms of numbers. Normally, you are familiar with basically sigma. Okay, 5 sigma, 3 sigma, this is what we talk about, okay? But observationally, the better way to characterize a model is good with the data or not is in terms of p-values. How many number of simulations match with the data, or how many number of data simulations match with the theory? This is what we do here in this plot. These are p-values, probabilities of model given the data, probability of data given the model. And we look at all the parameters. RTT is the ratio of odd even to the odd. And data says this is 0.79. So Planck data clearly says this, the significance of this number is more than 3.5 sigma. And you see it is exactly 20%. There is 20% excess of power in the odd multiples compared to even multiples. That's what I was talking about in the initial pictures, in the visual pictures of hot and cold mirrored structures in the CMB. And sorry, yeah. More parameters? No. I have direct sum inflation and standard inflation has the same number of parameters, NS, all the lambda CDM, no extra parameters. This is RTT is basically ratio of sum of power in the even to the sum of power in the odd. This is basically observation. People looked into it. It's not a parameter, okay? It is what is measured. So they look at how much power in the whole CLs. No, I'm not. Basically, theory just gives CLs, right? So you basically look at the same information of the CLs in different ways. This is one. This is another one. This is basically difference between CLs of even and odd. This is ratio between sum of even CLs and odd CLs. So these are all related to CLs, or odd and even CLs. These are not new. These are just different ways of characterizing observables, the data analysis, okay? Now, the important point is if you look at the low quadrupole and RTT, the probability of probability of direct sum inflation explaining the data is 650 times more than standard inflation. Okay, fine. Now, what is the intuitive picture of what is happening in this theory? Okay, we have universe expanding, quantum fluctuations generated during expanding universe, and inflation breaks time reversal symmetry, and the quantum fluctuations in this theory behaves like because the time reversal symmetry is broken, parity is broken. So we have a theory that if you have a symmetry, parity and time reversal symmetry in the background, quantum fields respect the background. If it is broken, your quantum field evolves differently at parity conjugate points in physical space. Because time reversal is broken, what evolves at x is different from what evolves at minus x. So this is the picture that is generating all these amazing fits with the data. Since I have less time, I will quickly go through the theory part. Just a comment, there are no other anomalies in the CMB. It's only parity. What we proved is that all the other anomalies related to hemispherical asymmetry and everything is dominated by the fact that the quadrupole is low and people did the biased analysis because there is no theory for them to guidance. So observational data, people need theory. Otherwise, there is no way to learn anything from observations. So what they have seen is that, okay, maybe there is an anisotropy. It's good, fancy to think of cosmological principle violation, but no. We proved that this anomaly is not there. Well, there are thousands of papers on this in the last 20 years. Okay. We have also prediction for primordial gravitational waves, but let me go to the theory part. How much time I have? Okay, thanks. Now, there is a paper by Einstein and Rosen in 1935 titled Particle Problem in General Relativity. And they tried to understand the concept of particle near a horizon, gravitational horizon. Of course, especially to Schwarzschild horizon, but I don't go to the details. They conjecture that a particle in physical world should be mathematically described by a bridge between two sheets of space-time. This is the statement. This is about quantum theory, particle problem in general relativity. It is nothing to do with classical theory, and do not get confused with wormholes. They came later from classical modifications of GR. These two brilliant guys worried about quantum mechanics and GR. When they focused how to understand quantum fields at the outside the social black hole, just outside the social black hole, they saw that there are two ways of explaining what is outside. This is related to this particular, what I call it, time reversal. And they could not understand how to make sense of particle, which can be either by one sheet of space-time, another sheet of space-time. They said universe must be one. There is only one physical universe. Somehow you need to describe particle as a mathematical bridge between two sheets of space-time. I repeat, this mathematical bridge, it's not physical. Okay, and they are doing quantum mechanics. Now, if you look at de Sitter space, this is what you take, right? If you say expanding universe, there are two ways of understanding expanding universe. T minus infinity to infinity, h greater than 0. T infinity to minus infinity, h less than 0. You reverse the arrow of time, you reverse the sign of h. It is still the same expanding universe. Expanding universe is characterized by the growth of the scale factor, nothing related to time coordinate appears in the metric. There are two ways of realizations. This is exactly PT symmetry. Okay, de Sitter space is exactly 12h square, h to minus h is the symmetry. So we have to look at carefully discrete symmetries. This is what Schrödinger wondered about in 1956, expanding universes, and he rejected the idea of two universes. There should only be one universe. He suggested, okay, fold the space-time and there should only be one universe. After almost 50 years, 60 years, Herr Toft in the understanding of black holes came to the same idea. How come you can describe a quantum field with two sheets of space-time? So, three Nobel laureates thinking about the same problem. No, they cannot be wrong. There is something fundamental they are really pointing out, and Einstein and Rosen exactly got the point. And if you look at quantum mechanics, what is the problem between gravity and quantum mechanics? Quantum mechanics is the first order differential equation in time, and all the equations you talk about gravity are the second order differential equations in time. And in quantum mechanics, you define a positive energy state, but you have to fix the arrow of time. If I change the arrow of time, then I need to change I to minus I to get the equivalent description. That means there are two time arrows to describe positive energy state. So the quantum mechanics has the same ambiguity which has been seen in all understanding of different space-times. That means we need to understand better quantum mechanics in a different way. So why do we require positive energy state by two arrows of time? Can we define positive energy state without referring to the arrow of time? This is what we do. We split the quantum state by two components, okay, which describe the quantum parts, which are states evolving in parity conjugate regions, and we combine them by direct sum. Each state, one state is a positive energy state, evolves forward in time in one Hilbert space. Another component evolves backward in time in another Hilbert space. These two, the combination of these two Hilbert spaces, direct sum. This is called super selection rules or super selection sectors in algebraic quantum field theory. We use that in the context of re-understanding quantum mechanics with PT symmetry. And this is what we call mathematical bridge that explains exactly the vision of Einstein and Rosen. Because I don't have time, let me give you this intuitive picture. This is what the direct sum Schrödinger equation. So basically, you think about a quantum harmonic oscillator, right? Like a simple pendulum. It goes like this. But we divide the state into two components. So it goes like this. But it is the same harmonic oscillator, just reformulated in a different Hilbert space structure that describes parity conjugate regions of physical space. We repeat the construction to quantum field theory because quantum field theory is CPT symmetric, nothing changes. De Sitter space-time, nothing changes. I am skipping a lot of details here, okay? I hope I conveyed the concept. We, of course, in this construction, okay, I have 5 minutes. Okay, in this construction, we preserve causality. So that remember, time is a very special status in quantum mechanics. Time is a parameter. Okay, then you can ask in quantum field theory, space and time are on equal footing. Well, true, but the way we combine special relativity and quantum mechanics by imposing a causality condition, we do not change the character of time. Time is not an operator in quantum theory. Time is a parameter. Space is an operator. You have a space operator and your quantum states takes eigenvalues of position, okay? Time is a parameter. Now, we split the quantum state into two direct sum components, which evolve forward and backward in time in the parity conjugate regions. And of course, these are two components of the same state, and we impose commutative relation. This is a new causality condition. So that means we have complete causality. The construction is just PT symmetric. And amplitudes can be understood in a CPT symmetric way, much more explicit in this construction. Now, we apply the same in the de Sitter space. Remember, de Sitter space has the PT symmetry, which is here, okay? You see, when you take this metric, this is conformal to Minkowski, and this has a symmetry tau to minus tau x to minus x, but you assume that tau has to be less than 0. How come quantum fields kind of choose tau less than 0? Because time is a special meaning. So that means you break the symmetry when we do standard quantization. But in this quantization, we take into account all discrete symmetries of the metric. But inflation breaks this symmetry, time reversal symmetry, by slow roll parameters. This exactly leads to parity asymmetric quantum fluctuations. And this is exactly generating parity asymmetry in the CMP. Now, and the question is, in this framework, horizon is understood as a mirror. Horizon mirrors the states, because horizon, when we say horizon, when we cross the horizon, basically we do a discrete transformation, discrete change of coordinates. Okay, you may understand, well, where is this in spatial coordinates? Spatial coordinates, there is a singularity, right? But you go to crucial coordinates. So there is a discrete step you take, and this is similar you do in de Sitter space. This construction recovers unitarity. That means pure states evolve into pure states for any observer who has a horizon. How do we do that? Every pure state, which is described by a density matrix, is split into the two direct sum component. Here I am speaking about in the context of Ringler spacetime, the left and right linear observer has information in the form of pure states. And the states are related by discrete operations. I'm finishing it. And the same thing goes here. The important conundrum of QFT in curved spacetime is unitarity. If we do not save unitarity, we cannot achieve quantum gravity. It's not my statement. It is basically follows from 1935, Einstein and Rosen. We have to pay attention to this, all these historical developments. We also did understanding of black holes and information paradox, taking these wonderful developments by Toft and in the context of gravitational back reactions. I don't have time to explain all these things. I just want to quote that we have a way to solve the unitarity and information paradox problem, and that is important. That's what takes us forward in understanding quantum gravity. Gravitational horizons are the most important. Our haunting questions now, for example, dark energy, it is related to the lambda cosmological constant. It is giving us a finiteness, because if you take the Hubble parameters, okay, asymptotically Hubble parameter go into constant. So there is a gravitational horizon which we need to understand to better understand dark energy. There are interesting proposals called black hole universe, but this proposal actually emerged from the first initial papers of Friedman in 1922, who formulated FLRW cosmology, but in a finite region of space. Universes are not infinite. Universe is only one, only finite. This is what everyone, the great minds in our history of physics, has taken into account. So horizons, gravitational horizons and quantum mechanics is a way forward to understand quantum gravity. The same thing goes to dark matter as well, because we have dark matter halos which are decoupled from the cosmic expansion. And George Ellis and Stoiger propose that there is a new concept of horizon, which are called matter horizon. Matter cannot escape from our local group to outside. So horizons are the most important thing. We need to pay attention to observations. Observations have to pay attention to theory. That's the way to move forward. This is the message I would like to convey. Thank you very much. Sorry for taking more time. But particle physics, you cannot see because PT symmetry is Minkowski's nature of Minkowski spacetime. The whole construction is understanding quantum fields in a background spacetime, and Minkowski spacetime is PT symmetric. And if you talk about charged fields, CPT symmetry. So we cannot see any. Yeah, it's in cosmological. In a dynamical spacetime, we will see all these symmetries broken. Yeah.
I'm not sure if you address the problem of the look elsewhere effect.
Well, look elsewhere effect in which context you are talking about? Well, there is a look elsewhere effect in the context of anomaly called the hemispherical power asymmetry. Hemispherical power asymmetry is about more power and less power in a particular direction. But we proved that this anomaly is not there because the anomaly, they framed it, you go to ecliptic plane and you do the lot of simulations of your theory, but you look at in each simulation, you look at only in one direction. But what we did, in each simulation, we looked at 1,000 directions. There is no bias of the inflationary, temperature fluctuations indicating a specific direction. Okay, there is no such effect. People say that, okay, there is a look elsewhere effect, so there should be this anomaly, but this anomaly is not there. It is dominated by biased statistics and also forgetting about the quadrupole is low in the data. Parity has no look elsewhere effect because parity is something you look at in all directions. There is parity. Parity has nothing to do with any specific direction because parity is different from rotations. So in no continuous rotation produce parity effect. But look, yes, exactly. This is the same. You have two models which you want to explain. The effect is a difference ratio of the p-values is 650 times. If you want sigmas, okay, which is not the correct way to do in observational people's opinion, but still it is more than 3.5 sigma.
It's like maybe searching for circle can be or signature.
No, I mean, you feel like, but I'm talking about the data. That's why I presented the data first without involving any theory. You put only one formula, okay, which is derived here, which has no new parameters. Okay, this is the formula we plug in there and just do the data analysis. How it is derived is different. Okay, you can propose another theory and fit the data because what we see is the data is super sensitive. If you deviate from this expression, you're gone. You cannot explain the data. So we give a new method to completely understand CMB issues, CMB anomalies, low multipole issues. Surely it's an open ground to understand better our quantum gravity, which is quantum fields in curved spectrum, linearized quantum gravity at linearized level. Okay. Thank you. Amount is exactly proportional to the slow roll parameters, which is basically how much you departure from de Sitter is what determines the parity asymmetry.
How do you characterize the amount? 5%?
Well, as I said, it's 20% effect because you see in the RTT, it is 0.79. So there is 20% more power in the odd multipoles compared to even multipoles. Yes, coming out of the theory. Yeah. Thank you. Basically, the operation we use to combine to split the quantum state into direct sum of two components. So direct sum is the operation. Yeah. We propose this. Sorry, I didn't realize.
Where do you put them?
Anyway.
Like this, it would work.
Yeah.
Okay, thank you. And this back and forth.
You can back and forth with this.
Also
The
this one.
down arrow will go.
Okay, okay, thank you. And okay. Okay. So in this talk, I would like to take up again the old subject of one loop divergences in quantum gravity, which I mean just a pure quantum gravity with a cosmological constant. So this is an old subject, but I would like to recompute some of the divergences using new methods based on the word-line treatment of the graviton. So this is, well, basically the points I wanted to touch upon. So I take up these one loop divergences in quantum gravity with cosmological constant. I want to systematize all the results to extract the gauge invariant meaning of the divergences and get new divergences, new coefficients, studying quantum gravity in arbitrary dimension with the new methods. So first I will present the result I wanted to obtain. Then I will go to the technical part, the methods I use to compute these divergences. The older methods are the Schwinger-DeWitt kernel approach, the standard one, which then I readapt using a calculational tool, which is the word-line path integrals. And so I derive some of these divergences with these methods. And then I go over to a new method, which is the treatment in first quantization of the graviton. This can be achieved using the so-called n=4 spinning particle that I will describe along the way. Some of these works have been presented in some of the papers with some students in Bologna and other collaborators that have been in Bologna also at some point in time. So the aim is to study the Einstein-Hilbert action in the Euclidean dimension. I use Euclidean dimension for simplicity, in the presence of a cosmological constant. So I want to systematize all the results, as I said, and get a new one. So lambda is the cosmological constant sitting here. This is the scalar curvature. And the classical equations of motion, of course, are obtained by varying the action and putting it equal to 0, obtaining the minimum. And these are the Einstein's equation. So there are no matter fields, just the cosmological constant. We know that if we take the trace, we see that the scalar curvature is proportional to the cosmological constant, is a constant then. And the metric satisfies, well, the Ricci tensor is proportional to the metric through a constant related to either R or lambda. So such metrics are called the metrics of Einstein spaces. So these solve the classical equations of motion, which I will use later on when describing the quantum theory. To study the divergences, here I get confused. To study the quantum gravity, the quantization of that model, one can view that as a usual quantum field theory, an interacting one, in which one can extract the propagator, the vertices from the action, and compute Feynman diagrams. We know that the theory is non-renormalizable in dimension bigger than 4. And the aim is to characterize the ultraviolet divergences. So I want to study the one-loop graphs with external gravitons, which are captured by the one-loop effective action. So the standard way to obtain this one is to use the background field method. I rename the metric small g as a big G. So this is the Einstein-Hilbert action. And then I do a quantum background split. There is a classical background, and then the fluctuation which I quantize with the path integral. Then the one-loop effective action is obtained, here the gamma of G, the one-loop effective action, is obtained by path integrating over these quantum fields after gauge fixing, but keeping only the quadratic part in the quantum fields. They will depend only on the background. And this amounts to compute some functional determinants. There is a determinant related to the kinetic term with interaction of the graviton, and one from the Fadeev-Popov ghosts.
And this is the pictorial way of describing the effective action, the one loop graphs containing the effective action. So from that formula, one can extract that taking the logarithm, one gets logarithm of determinants, which can be related to the trace of the logarithm of these operators. These are functional traces and functional determinants. And in the Schwinger-Dewitt approach, one parameterizes, represents the logarithm as an integral in proper time, represent this logarithm by this integral from 0 to infinity. Then one extends this formula to operators, the operators f and curly f, the graviton operator and the ghost operator, to obtain this form of the one loop effective action. There is the integration of the proper time from 0 to infinity. There are these traces of exponential minus operator times t. These are the traces of the hit kernel related to these operators f and curly f. So this is the expression that one would like to study. And so in general, this effective action is gauge dependent, depends on the gauge fixing procedure, but becomes gauge invariant if you use the equations of motion. We put it on shell. So I will use the Einstein's metrics to extract the gauge invariant meaning of the divergences. So this was the expression of the formal expression of the one loop effective action in terms of the hit kernels. And to study, here there are, in the integration of proper time, there are two extremes, the 0 and infinity. At 0, we see the ultraviolet divergences that emerge in this representation. At infinity, when the loops of this particle are very big, we see the infrared divergences. So I insert here a regulating mass from the infrared part, and I concentrate on the 0 integration region, where I want to extract the diverging pieces of this effective action. One can do then a small t expansion of this hit kernel in terms of the so-called Seeley-Dewitt coefficients. And in this expansion in powers of t, there is a leading term which can be extracted from the free hit kernel. And then there are this coefficient, an, the Seeley-Dewitt coefficient. For a small enough n, they parameterize the divergences of dual loop effective action. And so my aim is to compute these coefficients, to recompute them and extract their meaning, and get a new one from the method that I will describe. So a way to see these divergences, perhaps also from the fact that they diverge at t equal to 0, one can also use the integration of proper time, keeping this regulated mass, the infrared regulator, and we see that it emerges the gamma function, which diverges for sufficiently small number n for this Seeley-Dewitt coefficient. So we recognize, for example, for n equal to 4, there is n equal to 2, which gives the a mass-independent divergence, the logarithmic one. But then we know that there are quadratic, quartic, and so on. N equal to 6, there are the logarithmic divergences related to the A3 coefficient, and so on. Letting the dimension to become bigger, there are more diverging pieces that are related to this coefficient. So I've been computing this coefficient. Again, most of them were already written in the literature, but I put them on shell to extract the gauge invariant meaning. Here on shell means that I'm using the Einstein's metrics. And this is the result that I wanted to obtain. A0 counts just the number of degrees of freedom of the graviton. And here there are the numbers that you can read off. These are gauge invariant numbers that, in a sense, parameterize how pure gravity diverges. And other approaches to quantum gravity, this model should give the same number. They are gauge independent. Let me review some history about this coefficient, and also to make sure that they are correct. For example, at d equal to 4, those coefficients reproduce the number of degrees of freedom are 2. These are the quadratic divergences. These are the logarithmic divergences. This game was started by Toft and Veltman. They consider quantum gravity with lambda equal to 0. So in such case, also R is equal to 0. So this term is absent. Also, this one is absent. Remains only this square of the Riemann tensor, which becomes proportional to the topological Euler density. So it's a total derivative. And they said, okay, quantum gravity is one loop finite. Actually, it's renormalizable. You can have the
divergence is related to the cosmological constant, if you wish, to the quartic divergences. So for r equal to 0, well, we don't see this coefficient. And these were discarded. And you see this is all the result by Toft embedded here. Later on, Gibbons, Hawking, and Perry could compute with this function the precise coefficient sitting on front of the topological term, 53/45, which is reproduced here. Later on, Christiansen and Duff, they considered the theory with the cosmological constant. Now on shell, r is not anymore equal to 0. So this coefficient does not vanish. And no one recognized that the theory is not renormalizable. You would need the counter term proportional to r squared and so on. So at this point, people looked at, for example, going at two loop, Gorov, Sagnotti, Van de Ven found that at two loops also pure quantum gravity with the vanishing cosmological constant was diverging. People started to search for improved ultraviolet theories, going to supergravity, superstrings, and other more recent proposals that make the theory finite, in fact. But I want to stick with this pure quantum gravity. And so here we see that there are the matching with the old results of this coefficient that I was describing. If I go to 6th dimension, I kept the coefficient for arbitrary dimensions. Well, here we see the number of degrees of freedom of the graviton in 6th dimension. And here we see A3 is the logarithmic divergence. Well, to check with the literature, I could find only result for the vanishing cosmological constant. So setting lambda equal to 0, r is also equal to 0. So these terms are negligible. Using the topological Oriel density in 6th dimension, these two terms, different contraction of the Riemann tensor, becomes linearly dependent. And there is only this divergence appearing, which matches what was computed a long time ago by Van Nuys and well, corrected by Critchley, and then also recently studying amplitude from gravitons using some quantum field theoretical models. And so this we see that these are correctly reproduced by this coefficient. So these are what I call the gauge invariant coefficient, the way to characterize, let's say, how quantum gravity diverges in arbitrary dimensions. Of course, if we go to dimension bigger than 6, so we start, I consider even dimension, at 8 there are new logarithmic divergences, and so this is not complete, but up to 6 dimension, these are all the set of diverging pieces. A3 would be finite in 4 dimensions, so will not be related to any divergence. So these are the numbers I wanted to compute. Some of these were, of course, present in the literature, but they were not evaluated on shell, and there were misprints in the literature, so it was not clear which one would be trusted. For example, in the book by David, there are some numbers which were not correct. I could check that in 4 dimension, the correct numbers that I could use to abstract this gauge invariant coefficient were reproduced, for example, by Avramidi and a student of his. Okay, so this is the result for the gauge invariant divergences, and they characterize quantum gravity at one loop. And I consider it as a benchmark for alternative approaches to perturbative quantum gravity. The way I computed them is through different methods, like the standard hit kernel method pioneered by Schwinger and DeWitt. And then a similar related method in which I use the word line path integrals to compute the hit kernel. And then, in a sense, a truly first quantized approach, a particle model which reproduces the graviton. This is, in a sense, a different approach to quantum gravity. And I could check that, in fact, on shell, this gives the same result of quantum field theory. So this is the benchmark for testing new methods of describing quantum gravity, the graviton. So let me briefly review, well, a little bit the hit kernel method, and then the word line approach to the hit kernel is the method that I call 1 and 2. Before we saw that we had this representation of the one loop effective action in terms of these differential operators, F and curly F, related to the graviton and to the ghosts. Schwinger and later DeWitt interpret this operator as kind of fictitious quantum mechanical Hamiltonians, so that this will be Hamiltonians, and this will be the solution of the Schrödinger equation Euclidean time, the hit kernel, and we have to compute the functional trace on this Hilbert quantum mechanical model. And so this trace can be computed really using eigenvalues of the position operator. There can be discrete indices related to spin, so this would compute the trace. And the hit kernel would, well, this is the hit kernel at equally initial and final points, which are made the same to compute the trace, can be expanded for a small proper time. There is a leading term related to the free particle, and there are these Seeley-Dewitt coefficients. So a standard way of computing them is to see that these coefficients are, well, satisfy some recursive relations obtained from the Schrödinger equation or the hit kernel, the hit equation. And so you can compute them recursively. So this is, let's say, the standard method. A twist on this is to use the equivalence between operators and path integrals to compute this hit kernel, or the trace of the kernel, use a quantum mechanical path integral. Here, S is the quantum mechanical action related to the quantum Hamiltonian H. So if you know which is the classical Hamiltonian, the classical action related to the quantum Hamiltonian, you can compute the path integral with standard perturbative methods, for example, for a small proper time. To compute the trace with the path integral, use a periodic boundary condition. And with this method, you have to find the action, the classical action sitting in the path integral related to the quantum operator. To do this, to apply this to quantum gravity, it was, we found it easier to split the graviton into a traceless graviton and the trace of the gravity field of the edge fluctuation. And the operator on evaluated for the background which satisfies the equations of motion, Einstein metrics, well, give rise to these operators. There is the fluctuation of the traceless graviton. This is the operator, which should be seen as a fictitious quantum Hamiltonian in a given Hilbert space. This is related to the ghost. The ghost I call BC, like people do in string theory. And this is the scalar, the trace of the graviton is a scalar operator. And let me describe a little bit this classical action and the way I compute with the path integrals, this hit kernel coefficient, which gives the divergences of the effective action. The scalar particle, I would say, is the simplest system, but shows all the technical details of this word line approach. In flat space, you can consider a free Hamiltonian, p squared, with the mass equal to 1/2 in non-relativistic terms. So this is a simple Hamiltonian. And you know, the action is just, with this normalization, 1/4 of the velocity squared. Computing the trace for this system gives just the integration over space-time, related to the zero mode, if you wish. And there is this normalization. So this is standard path integrals of quantum mechanics. But in curved space, we know that the Hamiltonian has got some ordering problem. We know that the covariant Laplacian has got disordering in terms of the derivative operators. This is the scalar Laplacian, which in terms of the operator P and X means that there is this ordering, which fixes precisely this general covariant expression. There can be a scalar potential. And if you go to the classical limit, you know that the P and Q's commute, and the Hamiltonian is just this one. There is the square of the momentum with the metric plus the potential. And this is the Euclidean action. There is the kinetic term, which gives rise to a particle in curved space, of course, is a nonlinear sigma model in one dimension plus the potential. So this is the path integral we should compute. Well, for the trace of the graviton, we know that there must be a specific potential. So I put this specific potential in the action. To compute the path integral, we have to introduce some counter terms related to the word line path integral. This is a nonlinear sigma model, which has got some ambiguities, and we have to regulate it and fix the counter terms, let's say, to have precisely this quantum Hamiltonian. This counter term is finite, but takes into account the ambiguities that you have in quantum mechanics, let's say, the equivalent of the ordering ambiguities seen in a path integral. So using this path integral, I computed this trace of the kernel with the periodic boundary condition, and this is the result that you can get with the standard perturbative methods. So this is a contribution to the effective action. You continue, well, here I got some slides about some technical details. There are counter terms in this one-dimensional quantum field theory related to the fact that this is a nonlinear sigma model. Technically, it's super renormalizable, but there are some finite ambiguities. And the way you regulate the propagator and the vertices, when you contract them, you can find that there are product of delta functions that you have to regulate. There are corresponding counter terms that gives the same result. It is related to 3 different regularization schemes: time slicing, mode regularization, dimensional regularization on the word line. So they are bound to give the same result. Here there are another application of ghosts. The path integral measures contain a non-trivial expression related to the determinant of the metric at any point in the word line. And it's easier to exponentiate this with ghost fields so that the measure becomes translational invariant, and you can do perturbative expansion of the path integral. I use bosonic A ghost and fermionic BC ghost to create this square root of G, rather than 1 over square root of G and so on. The punchline is that this amounts only to shift the velocities by these ghost fields, so that when you do the perturbative correction, you see that if you contract with the contraction, velocity with velocity, the propagator gives a delta function, which is actually canceled by the delta function related to the ghosts. So one can see how the finiteness of the path integral emerges. Since we do also the path integral on circles, we do the one loop calculation in target space. We can, that is to say, use periodic boundary condition. You can fix a point on the loop and then make all the loops, and then integrate the loops the point on the loop everywhere to create all loops in space-time. If the point sits on the loop, this is what is called the Dirichlet boundary condition method. The quantum fluctuation around this constant is 0, so that q equal to 0, q equal to 1, you go back to the same point. Or we can extract, in a sense, the average position of the loop. And there is this non-local constraints on the quantum fluctuation. This is called the string-inspired method. So these are the technicalities in computing that path integrals. Then we have to also consider the other contribution on top of the trace of the graviton. There are the ghost fields and the graviton. On top of the position of these quantum mechanical particles, there must be also some extra degrees of freedom creating the spin of the particle, the spin of the ghosts, and then the spin of the graviton. The way to do that, to treat them, is to introduce extra degrees of freedom, in this case fermions, satisfying this anti-commutation relation, is to say creation annihilation operators in the Hilbert space. And if you consider x and lambda as a position and p and lambda bar as operators, as momenta, the function contains only, is only a function of the coordinates of x and lambda. Lambda is a Grassmann variable, so there is an expansion. And to keep only one index corresponding to the vector, we have to project to the one occupation number of this fermionic creation operator. And this can be done using a word line gauge field with the Chern-Simon coupling. So this is the projection mechanism that makes sure that in this slightly extended Hilbert space, we consider only wave function with one vector index. That is the ghost degrees of freedom. So again, we know which is the operator, which contains these degrees of freedom in addition. So this is the classical action. On top of the standard nonlinear sigma model, there are these additional word line fermions. A is this word line field that gives the projection. There is a Chern-Simon coupling, which is fixed to precisely project to occupation number 1. So we do the path integral to compute the trace of the kernel with periodic or antiperiodic boundary condition according if we do bosons of fermions. And this is the contribution that we get with this quantum mechanical approach. In a similar way, one does the most complicated particle, the tensor particle, the graviton. Here I use word line fermions, which have got a traceless symmetric indices to construct in the Hilbert space traceless symmetric tensor. There can be many occupation number. We again project to occupation number 1. This is the classical action to be put in the path integral. So it's a nonlinear sigma model with some fermions also coupled to the background curvature. There is the spin connection here because I use flat indices on the fermions, but curved indices on the coordinates, of course. And this is the result for this path integral, which I only quote for the moment, and I will give you perhaps some detail later. And so this summing up all three coefficients gives the total divergences that I described earlier for the one loop effective action. So I compute A0, A1, A2. For A3, well, I used this new approach, which eventually I tested also with the hit kernel method. And this is the truly, let's say, first quantized approach to the graviton. In a sense, it's more first principled. It's a little bit like in string theory. You quantize a particle model, which you know that through canonical quantization describe the graviton. You couple it to, okay, you couple it to the some background, little g mu nu. X and big G are X, some word line fermions, which describe the spin of the graviton, and some word line gauge field, which will implement the fact that this model describes the graviton. So in computing the path integral on the circle, I do the circle here in the background. There is a quantum field doing the one loop graviton, and these are the external graviton. So we extract this way the, in principle, if you could compute non-perturbatively the one loop effective action, in a perturbative expansion, I can extract the divergences. To give you a flavor of this word line model, let me go through some preliminaries. The scalar particle, bosonic particle, and the spin 1/2. So now we really quantize these relativistic particles, the coordinate of the word line, x mu. We quantize all the coordinates, but there is a gauge symmetry related to reparameterization invariant because I want to keep manifest covariance, at least Lorentz covariance. And we know that the constraint is related to the mass shell condition, p squared plus m squared equal to 0, implemented by the Einbein. If I eliminate the momenta, this is the action that I will put in the path integral. Eliminating also the auxiliary field, you get the standard action of a relativistic particle, the equivalent of the Nambu-Goto action of strings for the particle case. Studying the phase space action, you know that there is a constraint that at the quantum level gives rise to the Klein-Gordon equation. So this will be the canonical analysis done at this level. If I want to use the path integral in configuration space, I would use this action after gauge fixing the Einbein to give rise to the proper time. For the n=1 spin particle, this will describe the spin 1/2 fermion in target space. Well, on top of the coordinates, there must be some extra degrees of freedom creating the spin degrees of freedom. When you quantize them, you see that this gives rise to the gamma matrices, the representation of these degrees of freedom. And now to take care of the zero index needed for manifest covariance in target space, you have to impose another constraints, these constraints, which is actually the supersymmetric charge that squares to the Hamiltonian. These supersymmetric constraints gives rise precisely as a constraint in Dilbert space to the massless Dirac equation. So you see that this is a spin 1/2 field in first quantization. I consider only the massless case as an example. For the graviton, we need the 4 word line degrees of freedom for these spin fields. Basically, you're summing spin 1/2 plus spin 1/2 4 times to get spin 2. But then you have to do also some projection to eliminate the lower spin when you sum spins. So this is the model that was known a long time ago to describe the graviton in flat space. There are these constraints related to these gauge fields. And this is the supersymmetry algebra on the word line created by H, the SUSY charge, and this R symmetry charge. This is correct, but it's very rigid as a system. Describe the graviton only in 4 dimensions. It's difficult to couple to the background, but one can relax some of the gauging, and one can relax the R symmetry group to a certain parabolic subgroup. And this allows to extend the description to arbitrary D dimension And by BRST methods, one can see that can be coupled to a background, which satisfies Einstein's equation. Only in that case, the BRST symmetry has got a charge which squares to 0 for that background. So knowing this particle model that we know is consistent for the description of the graviton in Einstein spaces, I just do the path integral. There are some word line gauge fields which are gauge fixed to the certain moduli, the proper time, and the moduli related to the R symmetry group. There is a measure coming from the Faddeev-Popov determinant, and this is the gauge fixed action of the first quantized graviton. There must be some potential required by the BRST charge. There are the counter terms. And this is the measure that would arise from the Faddeev-Popov treatment, including also this Chern-Simon coupling. And okay, then we have got the path integral, and we can compute it, this word line path integral, and in a perturbative expansion in the proper time. This double angle bracket means perturbative expansion of the path integral. I do Wick contraction of the quantum fields using the free propagators. And then there is also the subsequent modular integration. I have to take the average over the angles, which here I call the theta and phi. While the last moduli, the proper time, I keep it as in the Schwinger representation of the effective action. And so this way I computed, we know that this model is consistent only on Einstein spaces, because only there the BRST charge, the quantum BRST charge is squared to 0. So if this is not the case, the effective action will depend on some, it will not be gauge invariant. But restricted to Einstein spaces, we computed the coefficient A3, which is consistent, well, is on Einstein spaces, and is the result that I presented earlier. Of course, we check that this coefficient you can obtain also with the standard if kernel method, and they matches. So we see that on shell, when we get the gauge invariant coefficient, we obtain the same result. Perhaps some technicalities in the way I do this calculation of the word line path integrals. To compute the hit kernel diagonal values, I use the Wick theorem for computing this exponential of the interaction action. This is the, if you wish, the Dyson formula. Yeah. I expand this interaction. You know, the action is just that of a nonlinear sigma model. I can expand the metric around the constant metric plus corrections. I use Riemann normal coordinates centered at the this initial equal to final points. For example, the first correction becomes from this extra term in the metric. There are the two velocity. So in terms of the quantum fluctuation, you get a 4-point coupling. And then you start to do the Wick contraction. You get QQ, Q dot, Q dot, QQ dot, QQ dot. Using the propagator, which I call this function, is called the delta. Here there are some divergences in which you contract velocity with velocity, which is canceled by the divergences related to the ghosts. Then there can be a finite remaining part, which is, however, taken care by the different regularization. There is another contribution in which you contract Q with Q dot twice. So these are the word line Feynman diagrams, if you wish, which are two loops. Well, these are actually 3 loops on the word lines, if you consider the power of H bar, which would sit there also at the classical level. No, so this is 2 loop, yeah. And okay, if you sum all these things, you do this simple integral on the word line, and you get this result that is the first leading term of this hit kernel expansion. So these are a little bit of a flavor of the way I would do this calculation in the word line methods. So detailed discussion of this path integral in curved spaces has been reported in this book that I wrote some time ago with Peter van Overnoysen, Path Integrals Anomaly in Curved Space, which now I take up again with a new monograph with Christian Schubert, in which I apply this method to word line path integrals applied for extracting quantities in quantum field theory. This should appear perhaps next year. So these are my conclusions. I've been systematized all the results in quantum gravity by computing this gauge invariant coefficient which characterize the one loop divergences of quantum gravity with the cosmological constant. I've been reaching up to A3, but keeping the dimension arbitrary. Up to 6 dimensions, these are complete. If you go above, there are additional divergences that appear. The most interesting, well, the new method I would say is the graviton treated in first quantization with this n=4 spinning particle. And the ideas for continuing along this line is to see if there are other applications of treating the graviton in first quantization, if there are easier things that can be computed with Worldline methods, or if there are also, is my interest to study other BRST model for particle system, relativistic particles. And this concludes my talk, which ends here. Okay, just in time. All right, it's fine. Yes. Yes, with the cosmological constant, pure, because the divergences are proportional to R squared. So you can renormalize. And then you solve it. Well, then, okay, you could say that then is renormalizable at one loop, absorbing to the cosmological constant. Okay, that can be also, but if you go to 2 loops anyway, it will not be renormalizable, so that is another matter. Here, the point is that I wanted to extract this precise coefficient to make sure that they are gauge invariant.
Thank you for the message. I have a question in your form for the general structure. Do you also, I don't see that you have terms, for example, like Ricci tensor. Can you explain why?
The Ricci tensor?
Ricci tensor, for example, cube. I saw you have terms for Ricci scalar.
Yes, because I compute all this coefficient when the Ricci tensor is proportional to the matrix times R over D, because I have to use metrics which satisfy the ground field equation. Otherwise, if I keep them arbitrary, they will depend the extra terms on the gauge fixing procedure that we've been adopting. So we expect that the effective action evaluated off shell is not gauge invariant. So this is the effective action evaluated on shell. And so all these non-gauge invariant pieces disappear. Sorry? Pure gravity with the cosmological constant. Well, it can be 0, the cosmological constant, but then no, they don't have to be Max-Planck symmetric. For example, this Riemann tensor could be more complicated than the one of maximal symmetric spaces. One there for S.
I'm wondering what the exact advantage of your method is over the standard heat. Because right now, computing a cube is relatively straightforward. So is your method just faster?
Well, that is just an academic interest. I mean, I wanted to see how you could describe the gravity in first quantization. And perhaps having different approaches can help in different situations. At the moment, I agree that there are no drastically new observables that you compute this way. Actually, other things are more complicated because, for example, I would not know how to compute more general one-loop graphs with external sources. But is yet a new method that, for example, you can check that, in fact, different description of, that you expect different description of quantum gravity should give the same results when you evaluate them on shell. So this is the point I was making, that different formulation of quantum gravity are bound to give these diverging pieces for this part. Yeah.
Thank you.
No. So let's send the speaker.
Thank you. Okay.
Well, I would like to conclude by thanking the local organizing community. Sorry for my non-Chinese accent. So, Kai Shen, Hao Hu, Jianping Jian, Yan Liu, Oleg Melishev. This one it's easier for me to pronounce. Abhishek Naska, he was over there. I think he left. Where? Oh, sorry, I didn't see you next. Xianyang.